How do factories make premium chocolate taste identical across millions of pieces? From roasting nuts and grinding cocoa to conching and precision depositing, every stage is measured to the second and degree. In this video, we follow Ferrero Rocher, Cadbury, and Toffifee from raw ingredients to sealed packaging, revealing the hidden production tricks that create that signature crunch. Ferrero Rocher is manufactured by assembling a layered sphere where a roasted hazelnut sits inside a wafer shell. The shell is filled with hazelnut chocolate cream. Then the whole piece is coated in chocolate and rolled in chopped hazelnuts before a final set and wrap. The process starts with hazelnut preparation because nut size and roast level define the center bite and also influence how the coating adheres. Raw hazelnuts are cleaned with screens and air separation, so stones and shells are removed. The nuts are graded by diameter, so the center nut fits the wafer cavity without forcing cracks. Roasting line heats the nuts to a target color and moisture. Roasting drives off water and develops aroma while keeping the nut interior crisp. After roasting, the nuts are cooled quickly, so residual heat does not soften the wafer later. Skins are removed after roasting because loose skin fragments create bitter specks and interfere with cream texture. Nuts pass through rubbers or abrasive rollers that loosen skins. Air aspiration lifts skins away from the heavier nut kernels. The cleaned nuts are then rescreened to remove broken pieces. Whole nuts are routed to center insertion. Broken nuts are routed to chopped nut streams or paste production. A portion of the roasted nuts is chopped for the outer layer. Chopping is done with calibrated cutters that create a narrow size band. The target size must be large enough to read as crunchy pieces. The target size must be small enough to adhere evenly to a wet chocolate surface. Chopped nuts are screened to remove fines because fines create dust and dull the finish. The chopped nut stream is held in dry, conditioned air so it remains free-flowing. Another portion of the roasted nuts is processed into hazelnut paste for the cream and chocolate phases. Nuts enter a grinding system where rollers or stone mills reduce them to a smooth paste. Grinding generates heat, so the paste line uses temperature control to avoid over-thinning. The paste is refined until particle size is below the gritty threshold. The paste is then held in jacketed tanks with slow agitation to prevent oil separation. Wafer production runs as a separate stream because wafer must be crisp and dimensionally stable. Wafer batter is prepared by blending flour with water and sugar and small amounts of fat. Mixing is controlled to hydrate flour while limiting gluten development. The batter is filtered to remove lumps that would block depositor nozzles. Batter viscosity is adjusted so it spreads evenly on heated plates. Wafer baking uses wafer irons that form thin sheets by heating both sides. The batter is deposited onto the plates and spread into a uniform film. Heat drives water out quickly and sets the wafer into a rigid, porous sheet. Baking time is tuned so the sheet dries to low moisture without scorching. The sheet exits and is cooled so it becomes crisp and easy to cut. To create the Rocher shell, the wafer is shaped into cups or hemispheres. One method presses warm wafer sheets into molded cavities and then trims the edges. Another method bakes wafer directly into formed shapes using shaped plates. Forming must avoid cracks because cracks allow cream leakage. The formed halves are inspected by size and by edge integrity. Wafer halves are then paired into hollow spheres. A joining step applies a thin line of adhesive cream or chocolate along the rim. Two halves are aligned and pressed together. Pressure is controlled so the seam closes without crushing the wafer walls. The joined shells are cooled briefly so the seam sets and the sphere stays rigid during filling. The filling cream is produced as a fat-based emulsion with suspended solids. Sugar and milk solids are blended with hazelnut paste and cocoa components depending on the target profile. The mass is refined so it becomes smooth and spreadable. Refining can be done with roll refiners or ball mills that reduce particle size. The cream is then conched or mixed under heat to remove moisture and to distribute fat. Final viscosity is tuned so it can be dosed into wafers without air gaps. Chocolate used for coating is prepared and tempered for stable crystallization. Chocolate is melted and filtered to remove unmelted particles. Tempering cools the chocolate and builds stable seed crystals. The chocolate is then brought to a working temperature that maintains flow. Viscosity is adjusted by temperature control and by cocoa butter balance. Stable viscosity is needed because coating thickness must be consistent. Filling the wafer sphere begins by dosing a layer of cream into the cavity. The dosing head inserts into the shell opening and dispenses a controlled volume. The shell rotates or indexes, so cream spreads along the inner wall. This creates a base that will hold the center nut. The volume is controlled to avoid excess that would squeeze out at closure. A whole roasted hazelnut is then placed into the center. Placement uses a singulation system that feeds nuts one by one. Each nut is aligned and dropped into the cream bed. The cream supports the nut and locks it in position. Nut placement must be centered so the final sphere balances during coating. Off-center, nuts create wobble and uneven chocolate thickness. After nut placement, the cavity is topped off with more cream. The second dose surrounds the nut and fills remaining void volume. The dosing profile is tuned to avoid trapping air around the nut. Air pockets can collapse during cooling and cause surface dents. The cream surface is leveled, so the opening can be sealed cleanly. Sealing closes the filled sphere, so the cream is enclosed. A wafer cap or a chocolate plug can be applied depending on design. If a wafer cap is used, it is bonded with a thin film of cream and pressed into place. If a chocolate plug is used, tempered chocolate is deposited to create a seal. The seal must be strong enough to survive later tumbling and coating. After sealing, the filled spheres are cooled to firm the cream. Cooling brings the fat phase into a stable crystal state. It also reduces cream tack, so spheres do not stick during transfer. Cooling is staged, so wafer does not absorb condensation. Humidity control matters because wafer crispness must be preserved. Once the centers are stable, the line moves into chocolate enrobing. The spheres pass through a chocolate curtain or a dipping system. Chocolate coats the surface and also acts as the adhesive for chopped nuts. Excess chocolate drains off as the spheres roll on a wire belt. A controlled vibration can smooth the coating and release trapped bubbles. Air knives can trim excess and define a consistent thickness. Immediately after chocolate coating, the spheres enter a nut coating stage. Chopped hazelnuts are applied while the chocolate is still wet. The spheres roll through a bed of chopped nuts, or nuts are showered from above. Rolling ensures full coverage across the sphere. Nut feed rate is tuned, so coverage is dense but not clumped. Excess nuts fall away and are recirculated after screening. Nut adhesion depends on chocolate temperature and set speed. If chocolate sets too fast, nuts will not embed fully and will shed later. If chocolate sets too slow, nuts can slide and form bare patches. The process balances chocolate temper and cooling tunnel entry, so the surface remains tacky long enough for nut embedding. After nut application, the pieces enter a cooling tunnel that solidifies the chocolate. The cooling profile is staged to promote stable crystals. Early cooling sets the surface quickly, so nuts lock in place. Later cooling pulls heat out, gradually, to avoid contraction cracks. Final exit temperature is set, so pieces are hard enough for wrapping. During cooling, the internal cream also equilibrates. The cream-fat network continues crystallizing and becomes firmer. This improves bite and reduces oil migration. Temperature stability prevents bloom risk and keeps the outer finish glossy. The wafer remains protected because the chocolate and cream act as moisture barriers. Some lines apply a final polish to reduce loose nut dust. A gentle tumbling or airbrushing step can remove unattached fragments. This step improves pack cleanliness and reduces debris in wrappers. It also reduces scuffing during downstream handling. Sorting and inspection occur before packaging. Vision systems can detect incomplete nut coverage and shape defects. Weight checks confirm fill and nut presence. Rejects are diverted so only uniform pieces reach wrapping. Metal detection can be used as a final integrity control. Cadbury chocolate begins as a controlled blend of cocoa components, dairy components, sugar, and fat that is refined into a smooth suspension, conched to stabilize flow and flavor, tempered to lock in stable crystals, then molded and packed, while temperature and viscosity stay inside a narrow window. Production starts with cocoa raw materials that arrive as beans or as processed cocoa ingredients, depending on the plant layout. When beans are used, they are cleaned first with screens and air separation, so stones and husk fragments are removed. The beans are then roasted in a programmed heat curve that drives off moisture and develops cocoa aroma while keeping scorch risk low. Roasting also makes the shells brittle, so separation is efficient later. After roasting, the beans are cracked and winnowed. Cracking breaks beans into nibs without pulverizing shells into fines. Winnowing uses airflow to lift lighter shell away from heavier nib. The nib stream is screened to remove oversized fragments that would strain grinders and to remove dust that would darken and overheat during milling. Nibs then enter grinding to become cocoa liquor. Grinding is a staged reduction where particle size drops while fat from the nib makes the mass flow. Early mills break nib into paste. Later mills refine the paste into a smoother liquor. Temperature is controlled because friction can raise heat and drive off aromatics. The goal is a stable liquor that is pumpable and consistent in solids and fat. Cocoa butter and cocoa powder streams are also managed. Cocoa butter is melted in jacketed tanks and filtered so no solid flakes remain. Cocoa powder is sieved to remove lumps that would create specks. These cocoa streams become levers for viscosity and flavor. More cocoa butter increases flow and melt. More cocoa solids increase intensity and thickness. Milk ingredients are prepared with the same attention to moisture and particle behavior. Milk powder is stored dry and sieved to break clods. Whey powders or lactose powders are handled similarly when used. These powders carry dairy flavor and also influence sweetness and caramel notes during later heating. Moisture in dairy powders must be low because water in chocolate drives thickening and seizing. Sugar is prepared as a clean, dry crystal feed. It is screened to control crystal size and remove agglomerates. Crystal size influences refining load and final mouthfeel. Fine sugar can reduce refining time but can increase dust and handling issues. Coarser sugar can slow refining and increase wear. The line selects a sugar specification that supports consistent refining performance. The first assembly stage is mixing, which creates a uniform pre-blend before refining. Cocoa liquor and melted cocoa butter enter a mixer and create a fat, continuous base. Sugar and milk powders are added gradually so they are wetted rather than floating as dry islands. Mixing uses a strong folding action to distribute powders through fat. The goal is a crumbly paste or thick dough depending on the recipe and the amount of fat present at this stage. In some milk chocolate processes, a crumb step is used to build characteristic dairy notes and to stabilize the milk solids. Crumb production combines milk and sugar with cocoa liquor or cocoa components and then heats the mixture to drive off water and develop flavor. The mixture is cooked until it becomes a dry or semi-dry crumb material. The crumb is then milled and later remelted into chocolate mass. This approach changes flavor and texture because it sets milk sugars in a different thermal history. Whether crumb is used or not, the downstream steps still require refining and conching. Refining is the step that turns the mixed paste into a smooth eating texture. Refining reduces the size of sugar and cocoa and milk particles so the tongue cannot detect grit. This is often done with 5-roll refiners or with alternative milling systems. In DUR, roll refining the paste passes between rollers with decreasing gaps. Each pass squeezes and shears particles smaller. The output becomes thin flakes because the mass leaves the final roll as a film that breaks off. Refined flakes have low free fat at their surface and are prone to holding moisture and air. They must be processed immediately into conching. Conching is a combination of mixing, shear, and controlled heat that changes both flavor release and rheology. In conching, the flakes are worked in a conche where paddles or rotors knead the mass. Heat keeps fat fluid and encourages volatile removal. Shear coats particles fully with fat, which reduces friction and lowers viscosity at a given fat level. Conching is often described as 2 overlapping goals. One goal is flavor smoothing by driving off unwanted volatiles and distributing aroma compounds. The second goal is flow control by reducing moisture and breaking down agglomerates so the chocolate becomes a stable suspension. Moisture control is critical because even small water content can cause thickening. Conches, therefore, manage airflow and temperature so water leaves gradually without overheating. During conching, emulsifiers can be added to fine-tune flow. Lecithin is a common flow modifier and it reduces yield stress by improving particle wetting. Another emulsifier can be used to reduce viscosity further at the same fat level. These additions are dosed late because early addition can mask conching effects and can change shear behavior. Dosing is precise because small changes alter how chocolate runs through pumps and through molding heads. After conching, the chocolate is held in storage tanks with gentle agitation. Tanks keep temperature stable, so the chocolate remains fluid. Agitation prevents separation and keeps the suspension uniform. Filters remove any foreign particles or unmelted lumps before tempering. At this stage, the chocolate is smooth and flavored, but it is not yet in the right crystal state for molding. Tempering is the controlled crystallization of cocoa butter that creates a stable set and a clean snap. Chocolate contains cocoa butter that can crystallize in several forms. Only specific forms give the desired gloss and contraction. Tempering builds a population of stable seed crystals and then holds the chocolate at a working temperature where these seeds guide solidification. Tempering is done in continuous tempering machines that heat and cool the chocolate in stages. The chocolate is first heated to melt existing crystals fully. It is then cooled while being agitated so crystals begin to form. It is then gently reheated to melt unstable forms while keeping stable seeds. The output is a chocolate that flows well, but contains the right crystal seeds. Process control uses temperature sensors and viscosity signals to maintain stability. Once tempered, the chocolate is ready for shaping. For bars, the main shaping method is molding. Polycarbonate molds move under deposit heads that meet a chocolate into each cavity. The depositor fills to a precise mass because bar weight must be consistent. Molds then pass onto a vibrating table. Vibration removes trapped air bubbles and levels the surface. It also helps chocolate flow into sharp corners and improves surface gloss. After vibration, molds enter a cooling tunnel. Cooling is staged so the surface sets without shock. As chocolate cools, it contracts slightly. This contraction helps release from the mold. Cooling zones remove heat gradually so internal stress remains low. If cooling is too fast, the bar can warp or show bloom later. If cooling is too slow, throughput drops and molds remain occupied. When bars have solidified, they are demolded. Molds are flexed or tapped so bars release cleanly. The bars then move to inspection conveyors. Vision systems can detect surface defects and missing corners. Weight checks can confirm deposit accuracy. Defective bars are diverted for rework. Rework. Chocolate is collected and remelted, then reintroduced upstream in controlled ratios, so crystal history does not destabilize tempering. If the product includes inclusions like nuts or crisp pieces, the process adds an inclusion stage. Inclusions are prepared by roasting or drying and then screening to a tight size band. They are added either into the chocolate before molding or sprinkled into molds before depositing. Inclusion dosing must be consistent because it affects bar thickness and cooling time. Inclusion surfaces must be dry because moisture causes thickening and can create voids. If the product includes layered fillings, the line uses sequential depositing. A chocolate shell may be deposited first and partially set. A filling is deposited next. Another chocolate layer seals the top. This creates a composite bar that requires additional cooling time and more careful temper control. Even then, the same fundamentals apply. Each phase must flow at the right viscosity and set in the right order. Once bars are fully set, they move to wrapping. Wrapping is a mechanical process that protects chocolate from oxygen and moisture and from handling marks. Bars are fed into a flow wrapper or into a fold wrap system depending on the pack style. The wrapper forms film around the bar and makes seals. Seal temperature and dwell are controlled so the film closes without wrinkles. Film tension is controlled so it does not crush the bar edges. Toffifee is manufactured by assembling a layered piece in a fixed cavity sequence, where a caramel cup is formed first, a hazelnut is seeded into that cup, a hazelnut cocoa cream is deposited around the nut, and a final chocolate cap is applied before cooling and tray packing. Production starts with preparing the two high-volume mass streams that define the piece. One stream is a caramel that must be firm enough to hold a cup shape, yet soft enough to bite cleanly. The other stream is a nut cream that must be smooth and pumpable, yet stable enough to keep its shape around the nut. A third stream is tempered chocolate for the cap and for any sealing functions. Caramel manufacturing begins with sugar and glucose syrup handling. Sugar is screened so crystal size is consistent and clumps are removed. Glucose syrup is held in jacketed tanks so viscosity stays stable for accurate pumping. Dairy components are prepared as a controlled liquid or powder stream depending on the recipe design. Fat is melted and filtered so it can be kneaded smoothly into the cook. Cooking is done in a continuous cooker or a batch kettle that is designed for high solids confectionery. The syrup phase is heated to dissolve sugar and drive off water. Solids level is the key target because it controls final chew and flow at the depositor. If solids are too low, the caramel will slump in the mold and stick in tooling. If solids are too high, the caramel becomes glassy and cracks when formed into thin walls. Temperature and residence time are tuned so browning develops to the desired level without scorching. As the cook reaches endpoint, the caramel is cooled to a working temperature where it remains plastic. Cooling is staged so viscosity is stable across the run. The caramel is held in a jacketed tank with gentle agitation to prevent skin formation. This tank feeds the forming depositor through heated pipes that avoid cold plugs. Flow meters and pressure sensors keep the depositor feed steady. Hazelnut handling runs in parallel. Nuts are cleaned and graded so the size band matches the cavity. Roasting drives moisture down and develops aroma while keeping the nut crisp. Cooling follows immediately, so residual heat does not soften caramel or melt cream fats later. Skin removal reduces bitter flecks and improves adhesion in the cream stage. Whole nuts are then singulated so they can be placed one by one. The hazelnut cocoa cream is prepared as a fat, continuous paste. Roasted hazelnuts are milled into a smooth nut paste with controlled temperature so oil does not separate. Sugar and cocoa solids and dairy solids are blended into this paste. Refining reduces particle size so the cream feels smooth rather than gritty. The cream is then mixed under controlled heat so viscosity becomes consistent and air is minimized. Emulsifiers can be introduced to tune flow and prevent oil bleed. The finished cream is held warm enough to pump but cool enough to keep flavor stable. Chocolate for the cap is produced and tempered to a stable crystal form. Chocolate is melted and filtered so no unmelted fragments remain. It is then tempered in a continuous tempering unit that heats and cools in stages. The goal is a chocolate that flows well but sets fast with gloss and clean release. Viscosity is monitored because cap thickness depends on flow through small nozzles. Assembly begins on a tray or belt line that carries a field of cavities. The cavities act as the master geometry for the product. Each cavity receives each component in sequence with tight timing. The first operation deposits caramel into each cavity as a measured shot. The shot is designed to form a cup rather than a flat puddle. This is done by using nozzle geometry and deposit motion that pushes caramel up the cavity walls. Immediately after deposit, a forming tool can shape the caramel cup. A punch or dome tool presses into the caramel to create a bowl profile. Tool temperature is controlled so caramel does not smear or stick. Dwell time is short, so the line speed remains high. The tool retracts and leaves a consistent hollow with a defined rim thickness. Caramel cup geometry is a major control point. Wall thickness must be thick enough to hold during nut insertion. Wall thickness must not be so thick that the bite becomes overly chewy. Rim geometry must be clean because the rim later interfaces with cream and the chocolate cap. If the rim is uneven, the cap can sit crooked and leave gaps. After cup forming, the cavities pass through a short cooling section. This cools the caramel surface to increase strength for nut insertion. Cooling is tuned to firm only the surface layer while keeping the bulk plastic. A fully hardened caramel would crack when a nut is pressed in. A too soft caramel would allow the nut to sink and deform the cup. Nut insertion follows. Nuts are fed from a singulator that orients each nut. A placement head drops or presses one nut into each caramel cup. Placement force is controlled so the nut seats at a consistent depth. The nut must be centered so the final piece balances. Off-center nuts can create thin caramel walls that tear. The nut is pressed enough to anchor without breaking the nut. Next, the nut cream is deposited around the nut. The depositor nozzle enters the cavity and dispenses a controlled volume. The cream must flow around the nut and fill the annular space. It must also avoid trapping air under the nut or along the cup wall. To control air, the deposit can be staged as a first ring and then a top fill. The nozzle motion can trace a small circle to wet the wall evenly. Cream viscosity is tuned for this step. If the cream is too thin, it floods and can overflow the rim. If it is too thick, it bridges and leaves voids. Void formation is a defect because it weakens structure and creates visual gaps under the cap. The line controls cream temperature tightly because temperature is the fastest way to shift viscosity without changing formulation. After cream deposit, the surface is leveled. A small leveling blade or vibration can flatten the cream surface. Leveling ensures the chocolate cap will sit evenly. It also ensures the cap seals the cavity edge without a high spot that would break later. Leveling is gentle because excessive vibration can move the nut and distort the cream ring. Chocolate capping follows immediately after leveling. Tempered chocolate is deposited as a disc onto the cavity opening. The disc must bond to the cream and rim and then set without cracking. Deposit weight defines cap thickness, which controls snap and protects the interior. If the cap is too thin, it can fracture during tray packing. If too thick, it can dominate the bite and slow setting. To achieve a clean cap, the chocolate is deposited at a temperature where it spreads slightly, then stops. The mold geometry helps define the cap edge. Some lines use a light vibration after capping to remove bubbles and ensure contact. Vibration must be limited because it can cause chocolate to run down the cavity walls and change appearance. 3 Musketeers bars are built by producing an aerated chocolate nougat center and then coating it in tempered milk chocolate before wrapping. The factory line is arranged so the nougat stream runs continuously into forming and cutting, while the chocolate stream runs continuously through tempering and enrobing. Both streams are tuned to match temperature, viscosity, and throughput, so the coating seals cleanly around the center without sink marks or edge splits. The milk chocolate coating begins with bulk ingredients staged for refining and conching. Granulated sugar is screened to a narrow particle size range so the roller refiner can produce a predictable grind. Cocoa liquor is preheated to lower viscosity and allow accurate pumping into the mixing tank. Cocoa butter is melted in jacketed vessels and circulated through filters to remove any solid crystals that could seed unstable texture. Milk powder is fed from sealed bins and is deagglomerated in a low shear disperser so it hydrates into the fat phase without forming dry nodules. Lecithin is held in a small day tank and is dosed late so it reduces viscosity after the primary particle size reduction. Vanilla or vanillin is stored as a concentrated liquid and is metered as a final flavor addition to avoid volatilization during extended heat exposure. A premixer combines cocoa liquor, a portion of cocoa butter, and sugar into a thick paste that can be refined. The paste is pumped to a 5-roll refiner, where it is squeezed into thin flakes that fracture sugar crystals and cocoa particles to a controlled fineness. The gap settings on each roll stage determine final particle size distribution, which controls mouthfeel and flow at enrobing. Refined flakes fall into a feed chute that meters into a conch. The conche applies heat and shear to drive off undesirable volatiles and to coat particles with fat. During conching, the remaining cocoa butter is added in increments to reach target viscosity without flooding the mass too early. Milk solids are blended in, so lactose and milk proteins are dispersed uniformly without scorching. Lecithin is added near the end to adjust yield value and plastic viscosity to match curtain requirements at the enrober. After conching, the chocolate enters a holding tank with gentle agitation that prevents separation and keeps temperature stable. From the tank, it flows to a tempering system that builds the correct crystal structure in the cocoa butter. The chocolate is heated to fully melt existing crystals, then cooled through a controlled zone to form stable seed crystals. It is then slightly reheated to remove unstable forms while preserving the stable fraction. The tempered chocolate exits at a narrow temperature band where viscosity is low enough for enrobing yet crystal content is high enough to set quickly on cooling. Inline viscometers monitor flow and trigger cocoa butter trim additions if the chocolate thickens. Filters ahead of the enrober remove stray solids that could block the curtain slot or imprint the coating surface. The aerated center starts as a sugar syrup system designed to whip into a stable foam. Granulated sugar is dissolved in hot water in a steam-jacketed cooker where temperature is driven to a target solids level. Glucose syrup or corn syrup is pumped in to reduce crystallization and to keep the finished nougat soft. The syrup is cooked under controlled pressure, so boiling is efficient and the concentration is repeatable. When the syrup reaches its target, it is discharged through a flash cooling step that drops temperature enough to prevent overcooking while preserving fluidity for mixing. The syrup then enters a continuous aeration mixer where it meets foaming proteins and fat. The foaming phase can be based on egg whites or protein blends that create a thin film around air bubbles. Liquid egg white is filtered and tempered so it whips predictably without breaking. If dried albumin is used, it is rehydrated under high shear and allowed to rest so hydration is complete before aeration. Proteins enter the mixer where high-speed rotors incorporate air while controlling bubble size distribution. Bubble size is managed by rotor speed, back pressure, and viscosity, which together determine the final density of the center. A small amount of fat is introduced to soften texture while not collapsing foam. Emulsifiers are used to stabilize the air cells and reduce drainage of the syrup phase. Cocoa or chocolate flavor components can be blended into the center so the interior tastes like light chocolate rather than plain vanilla. The aeration mixer operates as a pressurized system, so air injection and shear can be controlled precisely. Compressed air passes through sterile filters, then through a mass flow controller that sets the air rate per kilogram of nougat. The mixer creates a continuous foam stream that is metered to the forming section. Density is checked by inline measurement that compares mass flow to volumetric flow. If density drifts, the system adjusts air rate or syrup feed to recover. Temperature of the foam is controlled because warm foam collapses and cold foam stiffens before forming. A heat exchanger may be used on the syrup line to fine-tune final foam temperature at discharge. Once aerated, the nougat is sent to a depositor or extrusion head, depending on the specific forming method. In an extrusion layout, the foam is pushed through a slot die that creates a wide ribbon with a controlled thickness. The ribbon lands on a moving belt that has a release surface to prevent sticking. Belt speed is synchronized to extrusion flow, so thickness stays constant across the width. A leveling roller may follow to flatten the ribbon and to remove surface waves. The ribbon then passes under a conditioning tunnel where temperature is reduced gradually, so structure firms without creating a brittle skin. This conditioning step sets the foam walls enough for clean cutting. The nougat sheet is cut into bars using a guillotine or rotary slitter system. Longitudinal knives create parallel lanes with precise width. A transverse guillotine cuts each lane into individual pieces at the target weight. Knife timing is servo-controlled to keep cuts aligned even if belt speed changes slightly. Scrap from edge trim is collected and recycled back into the aeration mixer in controlled ratios so density remains stable. Bar weight is checked by dynamic scales that weigh each piece at speed. Out of tolerance, bars are removed by air jets that divert them into a rework stream. Before coating, the centers may pass through a brief pre-coat step. A thin layer of chocolate can be applied to reduce moisture migration and to improve adhesion of the final coat. This pre-coat is often applied as a bottoming film or a partial curtain. The centers then enter a short chill zone that sets the pre-coat so the bar can handle the stress of full enrobing. Surface temperature at enrobing is managed because a warm center can thin the coating and cause weak corners. A cold center can cause premature thickening and a rough surface. The line therefore targets a specific center surface temperature that balances flow and setting. Enrobing is performed by sending each nougat center through a chocolate curtain. The tempered milk chocolate flows from a header tank into a curtain slot that produces a uniform sheet of chocolate. The bar passes under the curtain and receives top and side coverage in a single pass. A bottoming wheel or bottomer reservoir coats the underside and closes the seam. Immediately after, coating the bar rides over a vibrating section that removes excess chocolate and levels the coat. Air knives blow controlled air across the surface to thin the layer and to sharpen edges. Air pressure is tuned so it does not expose the nougat at corners. The chocolate runoff is collected and returned to the tempering circuit where it is re-tempered before reuse. Decorative top marks can be added while the coating is still fluid. A striping head deposits thin lines of chocolate across the top to create the characteristic surface pattern. The striping chocolate is tempered separately to match viscosity and to prevent bloom in the stripes. Nozzles are aligned to bar lanes, so stripes land consistently. Flow is controlled by servo pumps that pulse for each bar group. Stripe height is kept low, so it does not crack during cooling or wrapping. After enrobing the bars, enter a cooling tunnel that sets the chocolate crystal network. Cooling is staged in zones to control contraction and gloss. An initial zone cools gently so the surface does not freeze before the interior sets. A middle zone cools more strongly to lock in crystal structure and to prevent deformation. A final zone equalizes temperature so the bar exits without condensation risk when exposed to ambient air. Conveyor speed and tunnel temperature define residence time. If residence time is too short, the coating remains soft, and fingerprints during handling appear as dull marks. If residence time is too long, the bar can overcontract and pull away at the seam. KitKat bars are manufactured by building crisp wafer sheets in continuous ovens, then layering them with fat-based cocoa cream before cutting fingers and enrobing them in tempered chocolate. The line is designed so wafer output is buffered to match chocolate throughput. The process starts with a batter system tuned for rapid baking and controlled porosity. Wheat flour is conveyed from silos to a sifter that removes bran specks and compacted lumps. The sifted flour drops into a day bin that feeds a high-speed whey hopper. Cornstarch may be blended into the flour stream to reduce gluten development and to increase snap after baking. Leavening is dosed in small quantities because wafer rise must be minimal and uniform. Salt is metered finely so it dissolves fully in the batter water phase. Sugar is used at a lower level than cake because wafer structure relies on starch gelation and moisture removal rather than sweetness. Liquid water is tempered to stabilize viscosity and to prevent seasonal drift in batter flow. Vegetable oil or melted fat is held in jacketed tanks and pumped with gear pumps for repeatable dosing. Emulsifiers are added to improve plate release and to help the batter spread thinly across hot surfaces. A portion of batter may include recycled wafer trim ground to a fine meal and hydrated to keep waste low without adding grit. Batter mixing is performed in a continuous mixer or in a batch mixer with rapid turnover, depending on line scale. Dry ingredients are blended first, so leavening and salt are dispersed before liquids arrive. Liquids enter through multiple injection points, so flour hydration occurs quickly without dry pockets. The mixer uses high shear at the inlet and lower shear near discharge to avoid excessive gluten formation. Batter temperature is controlled because warm batter thins and overspreads, while cold batter thickens and causes uneven fill. Viscosity is measured by inline torque or pressure drop and adjusted by microdosing water. A deaeration step may follow mixing to remove large bubbles that would create blisters in the wafer sheet. The finished batter is pumped to a feed manifold that supplies the baking machine with constant head pressure. Wafer baking uses paired heated plates that close to a precise gap and imprint a grid texture. The plates are heated by gas burners or thermal oil circuits and are held within tight temperature tolerances across the surface. Batter is deposited onto the lower plate by a dosing head that measures volume for each plate cavity. The top plate closes and spreads the batter into a thin layer that fills the pattern relief. Baking begins instantly as water flashes into steam and the starch begins to set. The plate set moves through a tunnel oven where heat continues to drive moisture out while browning remains controlled. Venting removes steam so it does not condense on cooler machine sections and drip onto new plates. Plate pressure and gap determine wafer thickness, which later determines finger count per bar and final snap. Bake time is tuned so moisture drops low enough for crispness, yet not so low that the sheet becomes brittle during handling. When plates open, the baked wafer sheet releases and is transferred onto a cooling conveyor. The sheet passes under fans that equalize temperature and prevent trapped heat from softening the crisp matrix. Sheet moisture is measured indirectly by near-infrared sensors that scan across width. Any drift triggers changes in oven speed or plate temperature to recover the target. Wafer sheets are fragile, so conveyors use low-impact transfers and short drops. Alignment guides keep sheets square for the next operation. Scrap edges and broken sheets are separated and routed to a grinder for controlled reuse. Layering begins with preparation of the cocoa cream that bonds wafer sheets into a multi-layer block. This cream is a fat continuous paste rather than a water-based filling. Sugar is milled to a fine powder and blended with cocoa powder to form a dry premix. Cocoa butter and vegetable fats are melted and filtered to remove crystals that would make the paste grainy. The dry premix is added into the melted fat in a mixing tank with strong agitation. The mixture then passes through a roll refiner or bead mill to reduce particle size and to improve spreadability. Lecithin is added late to reduce viscosity and help the paste wet the wafer surface quickly. Flavor is added at the end to preserve volatile notes. The finished cream is held in a jacketed buffer tank at a temperature that keeps it fluid, but not so hot that it seeps deeply into wafer pores. Cream application uses a spreader system with metering rollers. A wafer sheet enters the station and passes under a curtain or roller that lays down a precise film thickness. The film thickness is controlled by roller gap and by paste viscosity. Another wafer sheet is placed on top by a pick and place unit that aligns edges. The sandwich passes through a compression section that ensures full contact without crushing the wafer cells. This layering repeats to build a block with multiple wafer layers separated by thin cream layers. The number of layers determines the final finger height and bite. Registration is critical because misalignment causes exposed wafer steps after cutting and uneven coating. After stacking, the wafer block enters a setting tunnel where the cream partially crystallizes to lock layers together. Temperature is reduced in stages to avoid warping from rapid contraction. The block is supported on a flat belt to maintain planarity. Block hardness is monitored by deflection sensors that measure how much the block bends at a given support span. When the block reaches a target firmness, it moves to cutting. If the block is too soft, blades smear the cream and pull crumbs. If the block is too hard, blades chip wafer edges and create dust. Cutting converts the block into long logs and then into fingers. A first set of rotary knives or ultrasonic blades slices the block lengthwise into bars that match the finger group width. Blade spacing is adjustable for different formats, like 2-finger or 4-finger packs. A second cutter slices the bars into individual finger lengths. Blade timing is synchronized to belt motion to prevent diagonal cuts. Crumb extraction hoods collect wafer dust so it does not contaminate chocolate surfaces later. Trim pieces are segregated because they can be reworked into wafer meal or into cream base depending on quality. The cut fingers are transferred gently to avoid cracking along the wafer grid. Before enrobing, the fingers may receive a base coat to improve seam closure. A bottoming bath lays chocolate onto the underside as the finger rides over a wheel. The wheel transfers a film, and then excess is wiped to a controlled thickness. The pre-coated fingers pass through a short cooling zone so the base sets enough to support the full coat. Surface temperature is controlled because warm fingers thin the chocolate layer and cold fingers cause thick buildup at edges. Chocolate coating starts with production of the milk chocolate used for the shell. Sugar, cocoa liquor, cocoa butter, and milk solids are mixed and refined to a target particle size. Refining is done on roller refiners that produce flakes for conching. Conching applies heat and shear to coat particles with fat and to reduce harsh notes. Lecithin is added to tune flow for enrobing and to reduce yield stress. The chocolate is then tempered to create stable cocoa butter crystals. Tempering follows a melt-cool reheat profile and is controlled by temperature sensors and viscosity feedback. The tempered chocolate is held in a header tank that feeds the enrober curtain at constant pressure. Enrobing covers the wafer fingers with a continuous curtain of tempered chocolate. Each finger passes through the curtain and gets top and side coverage. A bottoming section ensures the underside is sealed and eliminates bare spots at the edges. Vibrating conveyors level the coating and release trapped air at corners. Air knives shape the final thickness and clear chocolate from the finger grooves where excess would bridge the separations. Runoff chocolate is collected and returned to the tempering loop so crystal structure remains correct. Some formats add a chocolate line between fingers to strengthen the breakpoints, and this is done by targeted deposition nozzles before final cooling. Cooling tunnels set the coating without causing bloom or warping. The tunnel is divided into zones that control the rate of crystal growth. Early cooling stabilizes the surface gloss. Middle cooling builds strength through the thickness. Final conditioning equalizes temperature so wrappers do not trap condensation. Conveyor speed sets residence time and is matched to coating thickness. If cooling is too aggressive, the chocolate contracts unevenly and can crack at the corners. If cooling is too mild, the coating stays soft and picks up belt marks. Snickers bars are assembled as a layered composite where a whipped nougat base is topped with roasted peanuts and caramel, then sealed in a tempered milk chocolate shell. Production begins by building ingredient streams that can run continuously at matched flow rates. Each stream is conditioned for temperature and viscosity so it can be deposited or extruded with stable geometry. The final bar depends on tight control of moisture because nougat must stay soft while caramel remains pliable and peanuts remain crisp. Milk chocolate for the outer shell is prepared first because it requires refining conching and tempering steps that run best as steady-state operations. Sugar is screened to remove hard lumps and to maintain consistent grind behavior. Cocoa liquor is warmed to reduce viscosity before blending. Cocoa butter is melted and filtered so the fat phase is uniform and free of seed crystals. Milk powder is sifted and deagglomerated to prevent specking in the finished coating. The ingredients enter a pre-mixer that produces a thick paste with evenly wetted solids. This paste is refined on roller mills or stirred media mills to reach a target particle size that balances smoothness with coating flow. Refined chocolate flakes drop into conchis where heat and shear coat particles with fat and drive off unwanted volatiles. Additional cocoa butter is added in stages, so viscosity is lowered without losing shear efficiency in early conching. Lecithin is added late to reduce yield stress and to improve curtain formation at the enrober. Flavor is added near the end, so aromatic compounds are not stripped by long residence at temperature. After conching, the chocolate is held in insulated tanks with slow agitation to prevent separation. The chocolate then enters a tempering machine that establishes a stable cocoa butter crystal form. Tempering runs in a melt-cool reheat profile where all existing crystals are first removed, then stable seed crystals are created, then unstable forms are melted out. The tempered chocolate exits at a narrow temperature window that is tuned to the enrober and to the cooling tunnel profile. Inline viscosity measurement checks for drift caused by temperature change or solid shift. If viscosity rises, the system trims with cocoa butter or adjusts temper temperature to recover flow. Chocolate is filtered before enrobing to prevent curtain streaks and to remove any particles that could block the slit. Nougat manufacturing begins with a cooked syrup that will be whipped into a low-density foam. Sugar is dissolved in water in a continuous cooker that controls concentration by temperature and flow. Glucose syrup is added to reduce sucrose crystallization and to keep the finished nougat tender. The syrup is cooked to a target solids level that defines final chew and shelf stability. The hot syrup is discharged through a heat exchanger that drops temperature to the range needed for mixing without oversetting. The syrup then feeds into a continuous aeration mixer where it meets proteins and fat. The protein phase can use egg albumin or alternative foaming proteins, depending on formulation. If liquid egg white is used, it is filtered and tempered for predictable whipping. If dried albumin is used, it is rehydrated under controlled shear, then rested to complete hydration. Proteins enter the mixer, where rotors incorporate air and create a stable bubble network. Bubble size is controlled by rotor speed and by back pressure at the discharge. Fat is added in a controlled stream to soften the foam walls and to improve chew without collapsing aeration. Emulsifiers stabilize the air cells and reduce drainage of syrup from the foam. Salt and flavor are added as concentrated solutions so they disperse instantly. The nougat exits as a continuous ribbon whose density is measured in line by mass flow and volumetric flow correlation. Nougat forming is commonly done by extrusion onto a moving belt. The extruder head uses a slot die to shape a wide sheet at a defined thickness. The belt speed is synchronized to extruder throughput, so sheet weight per length stays constant. A leveling system flattens the sheet and removes surface waves that would later telegraph through caramel. The nougat sheet enters a conditioning tunnel where temperature is reduced gradually to strengthen the foam network. The aim is to reach a firmness that supports topping without squeezing out air. If the sheet is too warm, peanuts sink and caramel spreads unevenly. If the sheet is too cold, the surface cracks under rollers and causes delamination after cutting. Caramel production runs in parallel because caramel requires controlled cooking and controlled final water content. Sugar and glucose syrup are blended and heated in a continuous caramel cooker. Milk or dairy solids are added depending on flavor and color targets. Fat is added to adjust chew and to reduce sticking during deposition. The cooker uses staged heating so the mixture rises to cooking temperature without scorching solids. Final concentration is achieved by driving off water to a precise solids level, which controls viscosity and final bite. The caramel exits through a flash cooler or scraped surface heat exchanger that reduces temperature while maintaining flow. The cooled caramel is held in a heated buffer tank with slow agitation that prevents skin formation and keeps temperature uniform. Viscosity is monitored because caramel that is too thin will flow off the nougat, and caramel that is too thick will not encapsulate peanuts properly. Peanut preparation is another parallel stream because the bar relies on a high fraction of nuts with stable texture. Raw peanuts are cleaned by screens and air aspiration to remove light debris. They are then graded by size, so the topping layer has consistent packing density. Roasting is performed in continuous roasters where time and temperature control drive flavor, development, and final moisture. After roasting, peanuts are cooled quickly to stop carryover heating and to preserve crispness. If salted peanuts are used, a fine salt solution or dry salt is applied in a tumbler and is then set by brief drying. Peanuts are then conveyed to a distribution hopper that feeds the topping system at constant rate. Vibratory feeders control flow and prevent bridging in the hopper. Layer assembly starts when the conditioned nougat sheet reaches the caramel deposition station. A spreader head or curtain depositor lays a uniform caramel layer across the nougat surface. Thickness is controlled by depositor slot gap and by pump speed. The caramel layer must be thick enough to bind peanuts and to form the characteristic chew band. Immediately after caramel application, peanuts are distributed across the surface. A scatter system uses vibrating trays and patterned gates to place peanuts evenly without bare zones or piles. A light compression roller follows to press peanuts into the caramel so they are partially embedded. Roller pressure is tuned so peanuts seat without crushing and without forcing caramel to the edges. excess peanuts are vacuumed or brushed off and recycled back to the topping hopper. The layered slab then enters a cooling and setting section that fixes layer geometry before cutting. Temperature is reduced to set caramel viscosity and to lock peanut position. Cooling is staged because sudden chilling can create internal stress that later causes layer separation. The slab is supported to prevent sag because caramel remains soft for a period. Sensors track slab temperature at surface and core because the slab is thick and cools slowly. Once the slab reaches the target firmness, it moves to slitting and cutting. Slitting divides the wide slab into lanes that match the final bar width. Rotary knives cut lengthwise and are adjusted to maintain clean edges through peanuts and caramel. Knife design is selected to handle nuts without chipping and without dragging caramel. Crumb and nut fragments are extracted to keep the line clean and to prevent inclusions in the chocolate coat. The lanes then pass to a guillotine cutter that cuts each lane into bar lengths at high speed. Cut timing is servo-controlled to match belt speed and to maintain consistent length. Off-size bars are diverted by a reject gate and are routed to rework streams, where they can be remelted into nougat or caramel depending on composition. Before enrobing many lines, apply a thin pre-coat or bottom coat to improve seal quality. A bottoming bath coats the underside and forms a base layer that helps close seams during full enrobing. The base coat is set briefly in a short cooling zone so the bar can be handled without smearing. This step also reduces exposure of nougat at the bottom corners, where enrober curtains can thin. Bar surface temperature is then brought to the target for full coating because temper performance depends on the heat load from the centers. The manufacturing process of Kinder Bueno begins with the preparation of the wafer batter. The primary ingredients, wheat flour, water, vegetable oil, lecithin, and leavening agents, are fed from storage silos and tanks into a stainless steel batching system. Each component is dosed with gravimetric precision, and the batch is mixed in a jacketed high-shear mixer. The flour is delivered via screw conveyors, water is flow-metered, and emulsifiers are introduced through liquid dosing pumps. Mixing time, rotation speed, and temperature are regulated to ensure that the batter reaches a uniform consistency suitable for rotary plate baking. Viscosity is continuously measured during mixing to maintain the desired flow behavior. The mixed batter is transferred to the baking system via diaphragm pumps. A rotary oven equipped with a sequence of upper and lower metal baking plates receives the batter through a synchronized volumetric depositor. The baking plates close, forming a mold that defines the half-shell structure of the wafer casing. The plates travel through the baking chamber, where they are heated via direct flame or electric elements. Internal plate temperature is maintained between 160 degrees Celsius and 180 degrees Celsius, with each shell requiring approximately 90 seconds of exposure to solidify and develop structural integrity. As the mold progresses through the oven, moisture is evaporated, and a thin, crisp wafer forms along the contours of the mold cavity. Upon completion of the baking cycle, the plates open automatically. Mechanical lifters remove the wafer shells and place them onto a wire mesh conveyor. The shells are cooled using forced ambient air delivered through adjustable nozzles positioned above and below the conveyor. The shells then enter a trimming station, where a high-speed rotating blade removes excess material from the shell edges to ensure uniform shape and dimension. The trimmed shells are rotated and aligned into uniform orientation using guide rails and belt positioners. The output is arranged into index stacks for timed transfer to the filling system. The hazelnut cream filling is produced on a separate line. Whole hazelnuts are delivered in bulk and transferred into a vibratory screening unit that removes any residual shell fragments or extraneous material. The screened nuts are routed through a mechanical conveyor to a continuous roasting system. Roasting is carried out in a rotating drum oven or a belt-type hot air roaster. The roasting temperature is controlled at 150 degrees Celsius to 160 degrees Celsius, with exposure times ranging from 20 to 25 minutes depending on kernel size. Roasted hazelnuts are cooled rapidly using counterflow ambient air to prevent oil migration. Blanching follows, using mechanical abrasion rollers to remove the skin. Blanched nuts are transported directly to the grinding section. Hazelnut grinding is conducted in 2 stages. The first stage uses a hammer mill or pin mill to reduce particle size to below 200 microns. The ground nut mass is then passed through a ball mill where particle size is further reduced to below 30 microns. The resulting hazelnut paste is transferred to a mixing tank equipped with counter-rotating blades. To this paste, specific quantities of refined sugar, vegetable fat, milk powder, and lecithin are added. The blend is agitated at a controlled temperature, generally between 35 degrees Celsius and 40 degrees Celsius, to produce a homogeneous, spreadable cream. Once fully emulsified, the hazelnut cream is transferred to buffer tanks maintained at a consistent temperature and mixed gently with slow-speed impellers to preserve structure. Wafer shells are filled using a precision depositor that aligns with each open wafer cavity. The hazelnut cream is pumped through heated stainless steel lines and dispensed in measured volumes through multiple nozzles. The depositor operates in cycles synchronized with the conveyor to allow for accurate deposit into each cavity. Each half shell receives a center-aligned column of cream filling, stopping short of the rim to accommodate sealing with the upper half shell. After deposition, the second wafer half is picked and placed onto the filled shell using robotic vacuum grippers. Sealing of the wafer is carried out with a dual pressure belt system that presses both halves together at controlled force. The sealed wafer unit is transferred to the next processing stage, where the internal coating is applied. A tempered chocolate mixture is circulated through a closed-loop system and delivered to the coating station. Each sealed bar passes beneath a chocolate curtain that applies a uniform internal chocolate layer around the wafer structure. An excess removal mechanism uses vibration and compressed air knives to prevent pooling or uneven distribution. The coated units then enter a cooling tunnel, which uses recirculated chilled air to bring the chocolate to a solid state without thermal shock. Tunnel dwell time is determined by belt speed and tunnel length, ensuring full crystallization of the chocolate layer. After internal cooling, bars are conveyed to the external enrobing line. This section applies the milk chocolate outer coating. The coating chocolate is prepared in advance by melting, tempering, and circulating through jacketed pipes maintained at 30 degrees Celsius to 32 degrees Celsius. The bars pass over a mesh belt conveyor under an overflow system, where chocolate is applied to the top, sides, and bottom simultaneously. The base layer is achieved through contact with a rotating chocolate-coated roller positioned beneath the belt. Excess chocolate is removed using oscillating air jets and a vibrating belt section. Once the milk chocolate layer is set, decorative stripes of dark chocolate are applied. A multi-head depositor positioned above the belt releases thin lines of dark chocolate in a controlled motion pattern, creating the characteristic curved stripe design. The application of stripes is synchronized with belt movement, and chocolate flow rate is controlled using peristaltic pumps and pressure regulators. The decorated bars are sent through a secondary cooling tunnel. This unit is divided into multiple temperature zones, gradually reducing the product temperature to ensure final structure without bloom or surface defects. After exiting the second cooling tunnel, the finished bars are individually wrapped using horizontal flow wrapping machines. Each bar is conveyed into a forming box where the wrapper film is folded around the product and sealed longitudinally by heated rollers. End seals are created using rotating sealing jaws that compress and heat seal the film ends. The temperature, jaw pressure, and dwell time are adjustable parameters based on film type and bar temperature. The wrapping material is pre-printed with branding and is fed from reels under tension-controlled rollers. Wrapped bars are grouped by rotary collectors and transferred to the bar collation unit. This unit counts bars and arranges them for packaging into twin packs or other desired formats. Grouped units are transferred into pre-formed secondary sleeves or cartons. These are closed with mechanical tucks or glue application systems, depending on the product configuration. The fully assembled and sealed cartons are discharged from the line at regular intervals. At no point during the process are the components exposed to cross-contamination, as each line is physically separated and supplied with dedicated material flow and thermal systems. The entire production line is configured to operate in continuous motion, with conveyors, deposition units, coating systems, and cooling tunnels fully synchronized. All components, from batter mixing to final wrapping, are connected through an uninterrupted mechanical chain, resulting in fully assembled, filled, coated, and wrapped Kinder Bueno units. Production of Bounty begins with the formation of the coconut filling. The core ingredient, desiccated coconut, arrives in bulk and is stored in sealed silos or stainless steel containers. The coconut is unloaded via vacuum conveyors into pre-cleaning units, where it passes through a series of vibratory sieves and magnetic separators to remove oversized flakes, fine powder, and metal fragments. After initial screening, it enters holding hoppers equipped with agitation paddles to prevent bridging during downstream feeding. From the hoppers, desiccated coconut is metered into large-scale batch mixers. In parallel, a blend of glucose syrup, invert sugar, and emulsified fats is prepared. Glucose syrup is stored in heated bulk tanks and is circulated through jacketed piping systems to maintain flow at a consistent temperature between 45 degrees Celsius and 60 degrees Celsius. The syrup is pumped into dosing vessels, where flow rate is precisely controlled via mass flow meters. Invert sugar, used for moisture retention, is added next. Solid fats, typically palm kernel or coconut oil, are stored in insulated tanks, liquefied by indirect heating, and pumped through a closed-loop recirculation system to maintain fluid consistency. The syrup-fat mixture is introduced into the batch mixer with the desiccated coconut. The mixer, usually a double Z paddle or ribbon blender, operates at low to medium shear to avoid breaking the coconut structure while ensuring even distribution of binders. The mixing chamber is jacketed to maintain the blend at 40 degrees Celsius to 45 degrees Celsius, aiding uniform fat dispersion. Mixing duration is controlled by programmable logic controllers and typically runs for 8-12 minutes per batch, depending on volume. Load cells beneath the mixer verify batch mass consistency. The completed coconut mixture is discharged through a pneumatically controlled gate valve onto a spreading conveyor. This conveyor leads to a slab, former consisting of a series of compaction rollers and edge formers. The mixture is shaped into a continuous ribbon or slab of fixed width and height. A top-leveling blade smooths the surface, and lateral guides maintain slab width, typically between 100 mm and 150 mm. Roller pressure and conveyor speed are adjusted to control slab density and moisture distribution. The continuous slab moves into a cooling tunnel to solidify the matrix prior to cutting. The tunnel uses chilled air circulated by variable speed blowers. Tunnel length ranges from 15 to 25 meters depending on line throughput, and internal temperature is maintained between 5 degrees Celsius and 10 degrees Celsius. Dwell time in the tunnel is approximately 3-5 minutes, enough to reduce the slab surface temperature to below 15 degrees Celsius. Exiting the cooling tunnel, the solidified slab is conveyed towards the portioning system. It first encounters a longitudinal cutting unit consisting of rotary disc blades that slice the slab into multiple parallel lanes. Blade spacing is adjustable based on final product width. These lanes proceed to the transverse cutting station equipped with servo-controlled guillotine knives. Blade actuation is synchronized with conveyor speed to ensure precise cut length, generally between 55 mm and 65 mm per piece. Each resulting rectangular coconut core is now a preform ready for enrobing. These preforms are transferred via a servo-driven indexing conveyor onto a perforated steel mesh belt leading into the enrobing section. In the enrober, the preforms pass beneath a tempered milk chocolate curtain. The chocolate, maintained at 30 degrees Celsius to 32 degrees Celsius, is pumped from a holding tank that continuously circulates it through a tempering unit. The tempering process cycles the chocolate through heating, cooling, and reheating, producing a stable beta crystal structure for gloss and snap. As the coconut bars pass beneath the chocolate curtain, they receive full top and side coverage. Simultaneously, a bottoming roller applies chocolate to the base through contact with the lower mesh belt, which has been pre-coated with a thin chocolate layer. Total chocolate deposition is regulated by overflow weirs and return flow pumps. After enrobing, the bars enter a vibrating section, which removes excess chocolate and promotes even distribution across the surface. Next, the enrobed bars pass under dual air knife systems, which blow away excess chocolate and refine the final bar shape. The air knives are positioned above and to the sides of the conveyor belt and deliver high-velocity air streams shaped by nozzles. Air pressure and flow direction are adjustable to control surface smoothing and eliminate drips or streaks. From here, the bars enter the cooling tunnel for chocolate crystallization. This tunnel is temperature zoned, typically starting at 12 degrees Celsius and gradually reducing to 6 degrees Celsius. Multiple air curtains prevent moisture intrusion. The cooling belt is constructed from food-grade plastic or stainless mesh and runs at a speed coordinated with enrobing throughput. Time inside the tunnel varies between 8 and 12 minutes, depending on bar dimensions and chocolate mass. Upon exiting the tunnel, the cooled bars are transferred via synchronized belts to the wrapping line. The wrapper feed system pulls pre-printed film rolls into a forming collar, where the film is shaped into a tube around each bar. The longitudinal seal is created by a heated roller or ultrasonic sealer. Transverse seals are applied at both ends by heated rotary jaws. The wrapping material is a multi-layer laminate typically composed of oriented polypropylene and metallized films for moisture barrier performance. The wrapping machine cuts and seals at rates exceeding 300 units per minute. Temperature, tension, and registration are electronically controlled. Eye marks on the film align the print with the bar position. Any deviation beyond +1 mm triggers automatic correction. Wrapped units are discharged via conveyor to a belt that aligns them for secondary collation. Depending on format, bars are grouped into twin packs or multi-packs. Mechanical pushers or robotic pickers load grouped units into cartons or wraparound sleeves. These cartons are formed from flat blanks fed from a magazine and folded using pneumatic actuators. Glue is applied at specific points by hot melt applicators, operating between 160 degrees Celsius and 180 degrees Celsius. Carton forming and glue compression are synchronized with product loading to ensure square, tight packages. Each carton is then indexed onto a conveyor for further grouping if needed. Although palletizing is excluded from this explanation, the output at this point consists of individual or grouped bounty bars, fully formed, enrobed, cooled, wrapped, and mechanically packed in a continuous flow operation. The production process is continuous, with coconut mass production, slab forming, cutting, chocolate tempering, enrobing, cooling, and packaging all connected via coordinated mechanical systems. Component flow is fully synchronized. All pumps, motors, conveyor drives, cutting blades, and enrobing units are driven by variable frequency drives and controlled via programmable logic controllers. Sensor arrays track mass, temperature, flow rate, belt speed, and chocolate level at multiple points. Each mechanical action is executed with predefined parameters for precise size, mass, and texture control. At no point is there any batch handling beyond the initial coconut sugar fat mixing phase. Once the slab is formed, the process is entirely linear and uninterrupted. Chocolate is continuously tempered and recirculated. Belt tension and alignment are automatically corrected by sensors positioned at key transition zones. All rotating equipment is balanced to minimize vibration and mechanical wear during high-speed operation. The only thermal processes are the initial cooling of the coconut mass to retain structural integrity during cutting and the two-stage cooling of the enrobed bar for chocolate crystallization. These are separated and isolated to prevent temperature overlap and ensure phase separation between fat-based ingredients and sugar syrups. Production of Baby Ruth chocolate bars begins with preparation of three major internal components: nougat base, caramel layer, and roasted peanuts. Each is manufactured separately in dedicated lines before being combined, enrobed, cooled, and wrapped. Nougat preparation begins by heating a sugar syrup composed of granulated sugar, corn syrup, and water in stainless steel cooking kettles. The mixture is continuously agitated with paddle mixers while being brought to a target temperature between 115 degrees Celsius and 125 degrees Celsius. The heated syrup is transferred via jacketed piping to a whipping kettle. In parallel, a protein solution, commonly egg white solids or milk protein concentrate rehydrated with water, is prepared in a separate mixing vessel and whipped at high speed using rotary whisks to introduce air and build foam structure. The hot syrup is gradually introduced into the aerated protein foam under continuous mixing. The injection is controlled with a metering pump to regulate flow rate and avoid protein collapse. Once combined, the mixture forms a dense but aerated nougat base. Additional flavoring agents, such as vanilla or milk powder, are introduced at this point. The nougat is discharged onto a cooling table or directly onto a continuously moving belt coated with release agent. The mass is shaped into a sheet using roller levelers that compress it to a uniform height, generally between 12 mm and 18 mm. Edge guides ensure consistent width. The nougat sheet passes through a cooling tunnel with forced air at 5 degrees Celsius to 10 degrees Celsius, solidifying the mass to prepare for the caramel layer. Dwell time in the tunnel is determined by line speed and product thickness. The cooled nougat sheet exits the tunnel and proceeds to the caramel application station. Caramel is prepared in a continuous cooker using a blend of glucose syrup, sweetened condensed milk, sugar, and butterfat. The ingredients are heated in a scraped surface heat exchanger where temperature is raised to 115 degrees Celsius, 120 degrees Celsius, allowing moisture reduction and Maillard reaction for color and flavor development. The cooked caramel exits through a static mixer and flows into a deposit manifold. Caramel is applied in a controlled layer onto the surface of the moving nougat sheet. A spreader bar or leveling roller ensures even thickness, typically between 5 mm and 8 mm. The sheet, now composed of nougat and caramel, passes through a secondary cooling tunnel to lower the temperature of the caramel to a semi-firm consistency. Cooling prevents deformation and facilitates cutting. At the peanut feeding station, roasted peanuts are applied onto the tacky caramel layer. Peanuts, previously roasted at 150 degrees Celsius, 170 degrees Celsius for 20-25 minutes, and cooled, are distributed from a hopper via a vibratory feeder. They are released through multiple chutes spaced laterally to ensure even coverage. A compression roller lightly presses the peanuts into the caramel, anchoring them mechanically. Excess or misaligned peanuts are removed by a combination of rotating brushes and air jets. The layered slab, now consisting of nougat, caramel, and embedded peanuts, proceeds to the portioning station. First, longitudinal cutting blades divide the sheet into multiple lanes, matching the width of the final bars. Rotary disc blades mounted on servo arms maintain cutting precision at high speeds. Next, transverse cutting is performed with guillotine knives that are synchronized with belt speed to produce exact bar lengths. Standard bar length ranges between 80 mm and 100 mm, depending on pack size. Each individual bar is spaced out on a conveyor and conveyed to the enrobing line. Enrobing is performed using milk chocolate prepared in tempering units. Solid chocolate blocks are melted in jacketed tanks at 45 degrees Celsius, 50 degrees Celsius. Melted chocolate is tempered using a 3-stage heat exchanger that brings the temperature down to 28 degrees Celsius, 30 degrees Celsius, before raising it slightly to 31 degrees Celsius, 32 degrees Celsius, optimizing crystal structure. Tempered chocolate is pumped to the enrober and flows over a curtain that uniformly coats the top and sides of each bar. The underside is coated by the bar contacting a chocolate film spread onto the mesh belt. The enrober uses a closed-loop recirculation system with a filter to remove solid debris such as peanut fragments. Chocolate viscosity is continuously monitored and adjusted by recalibrating the temperature or adding cocoa butter as needed. As the enrobed bars exit the curtain, they pass over a vibrating section that removes excess chocolate and evens out the coating. Air knives located above the belt blow off remaining drips and define the shape of the chocolate coating. Decorative top striations are formed by additional nozzles or vibrating wires that create surface patterning before the chocolate solidifies. Coated bars enter a cooling tunnel that is divided into multiple thermal zones. Temperature decreases gradually from 12 degrees Celsius to 5 degrees Celsius along the tunnel length. Air is dehumidified to prevent condensation and maintain surface gloss. Conveyor belt speed is regulated to maintain a dwell time of 10-14 minutes, allowing full crystal formation within the chocolate and ensuring coating integrity. After cooling, bars exit the tunnel and proceed directly to the wrapping system. Horizontal form-fill-seal machines handle individual wrapping. Printed film is fed from a roll and shaped around the bar using a forming collar. Longitudinal seals are made with heated rollers, and transverse seals are applied with rotating jaws. Seal parameters are set according to film type, typically biaxially oriented polypropylene. Eye mark sensors on the wrapper film ensure print alignment with bar positioning. Wrapped bars are discharged from the flow wrapper and directed onto collection belts. Depending on final packaging format, bars are grouped into singles, multi-packs, or inserted into cartons. Collation is handled by diverters and indexing conveyors that control product spacing and group counts. Cartoning is performed using automatic cartoner machines that erect, fill, and close cartons in one continuous motion. Hot melt glue is dispensed by nozzle applicators to seal carton flaps. Carton size and closure mechanism are adjusted based on product format. At this stage, the complete Baby Ruth bars have undergone mechanical and thermal transformation from raw syrup, milk solids, and nut ingredients into structured, layered, enrobed, and wrapped units. From initial syrup cooking to final wrapping, all steps are continuous and synchronized by servo-driven machinery, sensor-guided conveyors, and recipe-controlled dosing systems. No manual handling is present between slab formation and wrapping. All ingredient transitions are facilitated through pumps, screw feeders, and belt conveyors. Mixing, cooking, spreading, cooling, cutting, coating, and wrapping occur in physically distinct but functionally integrated process zones. The nougat structure is controlled by syrup concentration, aeration speed, and protein matrix strength. Caramel consistency is determined by temperature profile and solids content. Peanut adhesion is achieved by compression into a semi-set caramel phase. Chocolate crystallization is stabilized by controlled tempering and gradual cooling. Final bar geometry is maintained by precision portioning and belt tracking. Line speeds are configured to produce hundreds of bars per minute, with each step calibrated for thermal load, product viscosity, mass consistency, and dimensional tolerance. The entire operation functions as a continuous flow line driven by precise thermal, mechanical, and depositional parameters. The result is a consistently shaped, layered, and enrobed chocolate bar manufactured through a sequence of interdependent, high-speed industrial systems. The process begins with the preparation of the core ingredient, the peanut butter filling. Whole, dry roasted peanuts are delivered in bulk to the facility. These peanuts first enter a vibrating conveyor that removes loose skins and broken fragments. They pass under a high-powered magnet to eliminate any residual metallic particles. Then, the peanuts are gravity-fed into a stainless steel grinding chamber. Inside, large rotating blades crush the peanuts under high torque. The first grind reduces them to a coarse paste, maintaining some granular texture for mouthfeel. The paste is then pumped into a second stage grinder, equipped with finer burrs, reducing the particle size to below 20 microns. During this stage, a metered flow of salt, sugar, and hydrogenated vegetable oil is introduced via precision-controlled valves, ensuring consistent viscosity and sweetness across all batches. The resulting emulsion is routed through a jacketed pipe system, maintained at a specific temperature to keep the filling fluid enough for metering. This peanut butter flows into a holding tank fitted with an agitator that constantly stirs the mixture to prevent separation. The tank is linked to a high-speed depositor, which measures and dispenses precise volumes of the filling for the next stage. However, before the filling is used, the outer shell of the cup must be created. The outer chocolate coating begins with the mixing of ingredients: chocolate liquor, cocoa butter, milk solids, and sugar. These ingredients are loaded into a large-scale conche, a machine with heavy rollers that knead the mixture continuously for up to 12 hours. The conching process smooths out the texture and volatilizes undesirable flavors. After conching, the chocolate is pumped through a series of heated pipelines into a tempering unit. This unit cycles the chocolate through controlled heating and cooling zones to encourage the formation of stable cocoa butter crystals. This tempering process is crucial for creating a glossy finish and a crisp snap in the final product. Tempered chocolate is then delivered into the cup-forming system. Small polycarbonate molds, arranged in a continuous chain, move along a conveyor. At the first station, the molds are vibrated to eliminate air and then receive a precise amount of tempered chocolate. The molds pass beneath a rotary spinning unit that evenly distributes the chocolate along the interior walls, forming the shell. Rapid air jets cool and solidify the shell as it moves to the next station. Once the shell is set, the molds proceed to the filling line. Here, servo-controlled nozzles descend into each chocolate cavity and inject a precise volume of peanut butter filling. The temperature and flow rate are tightly regulated to ensure smooth deposition without overflow or disruption to the shell's integrity. As the filling sets, the molds continue moving to the capping station. At the capping station, a second layer of tempered chocolate is applied over the exposed filling to seal the cup. A gentle vibration removes trapped air and levels the surface. The molds then enter a refrigerated tunnel where they spend several minutes at sub-zero temperatures. This rapid cooling locks the structure in place and allows for demolding without cracking or warping. After cooling, the mold chain reaches the demolding station. A synchronized pusher mechanism nudges each mini cup out of its cavity. The cups drop onto a soft conveyor belt lined with food-grade cushioning material. From here, they are directed to an inspection line equipped with high-resolution cameras. These cameras scan each unit for surface defects, incorrect shape, or incomplete sealing. Any product that falls outside tolerance is automatically ejected via an air-jet mechanism. Perfect cups continue along the belt to the wrapping system. The cups pass through a vibratory feeder that aligns them uniformly before entering the wrapping carousel. Here, pre-cut foil wrappers are fed from a roll and precisely positioned. A series of rotating arms wrap the foil around each mini, folding it into the familiar pleated skirt pattern. Heat-sensitive adhesives are applied in microdots to secure the foil in place without melting the chocolate underneath. The wrapped minis are then transferred to a bucket conveyor, which lifts them vertically to the weighing and portioning unit. This section uses a combination of multi-head weighers and vibration channels. Each head calculates the exact weight of its portion and releases it into a funnel only when the total matches the predefined package weight. The minis fall into open pouches below, which are already held in place by a form-fill seal machine. As each pouch is filled, it moves to the sealing station. The top edges are pressed together between heated jaws that apply pressure and temperature simultaneously, creating an airtight seal. Excess air is evacuated prior to sealing to prevent bloating and ensure compact packaging. After sealing, each pouch is marked with a lot code and timestamp using a thermal inkjet printer for traceability. The sealed pouches drop onto a short accumulation conveyor that buffers the output before transferring them to a final packing station. Here, robotic arms pick up the pouches and place them into pre-formed cartons with precise orientation. The cartons are closed, sealed with hot melt adhesive, and stacked in layers onto shipping pallets using a gantry-style palletizer. Each completed pallet is automatically stretch-wrapped for stability and sent to storage for distribution. This entire process is governed by a centralized control system that monitors temperature, humidity, belt speed, deposition volumes, and flow rates. Real-time sensors feed data to a control panel, allowing technicians to make micro-adjustments and ensure batch-to-batch consistency. The system can run continuously for up to 24 hours without stoppage, capable of producing tens of thousands of minis per hour. Next, the focus turns to how raw materials are handled before entering production. Peanuts arrive in bulk tankers and are gravity discharged into underground silos lined with food-grade epoxy. Each silo is equipped with aeration systems to prevent moisture accumulation and ensure uniform temperature. The peanuts are pneumatically conveyed through stainless steel tubing into a vibratory feeder that meters the flow into a destining machine. This device uses oscillation and airflow to separate stones, soil particles, and foreign debris from the peanut stream. From there, the peanuts pass through a laser optical sorter that uses infrared and visible spectrum imaging to detect discolored or malformed nuts. High-speed air nozzles eject any flawed peanuts in milliseconds. Only uniform, high-grade peanuts proceed to the roasting unit. This unit is a continuous belt roaster with adjustable zones. Peanuts pass through multiple chambers where hot, dry air is circulated by impeller fans. Temperatures are carefully staged, rising from 120 to over 160 degrees Celsius, which drives out moisture and enhances flavor through Maillard reactions. Once roasted, the peanuts are cooled, using forced ambient air passed through a vibrating bed. This prevents residual heat from continuing the roast and ensures a consistent final color and texture. The roasted peanuts are then fed through a skin removal drum that uses abrasion and airflow to strip the outer skins. The clean peanuts are conveyed via vacuum lift to the grinding area, where the previously mentioned multi-stage grinding begins. Simultaneously, chocolate ingredients are stored in segregated silos and tanks. Sugar is kept in dehumidified environments to prevent caking. Milk solids and cocoa powder are transferred via screw augers into premix hoppers. Cocoa butter and chocolate liquor are maintained in heated jacketed tanks to remain fluid. All ingredients are automatically metered and conveyed to the conche for blending. The chocolate mass, after completing the conching phase, enters a holding tank fitted with constant agitation paddles to maintain homogeneity. From there, it's pumped into a multi-stage tempering system composed of a series of heat exchangers and temperature control zones. The chocolate is first heated to melt any remaining crystals, then rapidly cooled to initiate the formation of stable crystal forms, and finally brought back to a processing temperature that maintains its tempered state. This temperature is precisely held between 30 and 32 degrees Celsius, depending on the chocolate formulation. This tempered chocolate flows directly into a reservoir connected to the cup-forming depositor. This depositor features a rotating drum fitted with piston cylinders, each calibrated to dispense exact volumes of chocolate into the molds. As each polycarbonate mold tray moves beneath the depositor, the nozzles descend and fill each cavity with a metered dose. Immediately after deposition, the molds enter a vibrating station. Here, high-frequency vibrations cause the chocolate to flow evenly into the intricate cup recess, eliminating trapped air bubbles and ensuring the chocolate climbs uniformly up the sides. Next, the molds travel through a cooling tunnel set to gradually decrease the temperature. The tunnel is segmented into thermal zones that first solidify the outer edges of the chocolate shell and then slowly cool the entire form to prevent cracking. The movement through the tunnel is continuous and synchronized, with the chocolate shells emerging after a calculated duration with fully formed, hardened interiors. At this point, the molds reach the peanut butter filling station. A separate heated pipe system maintains the filling's viscosity, keeping it soft enough to flow but not hot enough to melt the chocolate shell. This balance is crucial. The filling enters a pressurized manifold which feeds into a multi-head depositor equipped with servo motors. Each head aligns perfectly with the center of the chocolate shells and injects the filling with millisecond precision. The volume of filling is less than the total cavity depth, leaving room for the chocolate cap that will follow. As soon as the peanut butter is deposited, the mold trays pause momentarily while a burst of cool air is blown across their surface. This quick setting step helps firm up the top surface of the filling, preparing it for the capping stage without blending into the final chocolate layer. The capping process begins as the molds continue along a conveyor that passes beneath a second chocolate depositor. This unit mirrors the cup-forming depositor in design, but delivers a thinner stream of chocolate, just enough to create a smooth, flush surface over the peanut butter. The moment the cap is applied, the trays enter a second cooling tunnel with slightly lower humidity and temperature levels. This cooling tunnel runs longer than the first, allowing the entire assembly, base shell, filling, and cap, to solidify into a single bonded unit. Once fully cooled, the molded cups must be extracted without damaging their structure. At the demolding station, each polycarbonate tray is inverted over a soft silicone belt. Pneumatic actuators positioned above each cavity deliver a gentle burst of compressed air to eject the cups downward. The silicone belt cushions the fall and conveys the cups to a visual inspection zone. This inspection zone features an array of high-speed cameras positioned at multiple angles. Each cup is rotated in place as cameras scan for surface imperfections, discoloration, uneven capping, or malformed shapes. The system uses real-time image recognition algorithms to detect defects within milliseconds. If a unit fails inspection, it is marked by a food-safe dye jet and then removed further down the line by a robotic picker. Passing the inspection, the cups proceed into the foil wrapping module. The cups are gently aligned by centrifugal force in a rotating disc feeder. As each cup enters the wrapping station, it passes through a timing screw that spaces them evenly. Each cup is paired with a pre-cut foil sheet fed from a stacker. A vacuum arm lifts the foil and places it atop the cup just before it enters the wrapping drum. The wrapping drum rotates at high speed. As the cup and foil pass through its internal channels, shaped mandrels fold the foil around the cup. Fine-toothed wheels pleat the edges in the signature ruffled pattern. During this rotation, a micro dot of adhesive is applied to the final fold, locking the wrap in place. The entire wrapping process takes less than 1 second per unit, with the machine capable of processing several hundred cups per minute. After wrapping, the minis exit onto a multi-lane conveyor. These lanes gradually converge into a single stream, where the minis fall into a vibratory channel that leads them to the multi-head weigher. This weigher consists of a circular array of hoppers, each continuously filled with minis. Load cells beneath each hopper constantly monitor the weight. The system's algorithm selects a combination of hoppers that together match the target pouch weight most precisely. Once the optimal combination is determined, the corresponding hoppers release their contents into a chute, which guides the minis into the waiting pouch below. The pouch is held open by mechanical grippers in a vertical form-fill-seal machine. This machine forms the pouch from a continuous roll of pre-printed laminate film. As the film unwinds, it passes through a forming collar that folds it into a tube. Vertical heat seal jaws bond the overlapping edges of the tube, while horizontal jaws seal the bottom to create the pouch base. The minis are then dropped into the open pouch, and the top is sealed immediately after filling. The sealing jaws apply precise heat and pressure, creating a strong, airtight bond. After sealing, each pouch travels under a printer head that marks it with production data, including time, date, and batch identification code. These markings are made using thermal inkjet or laser etching systems, depending on the packaging material. The printed pouch then passes through a final check weigher to confirm the net content. If underweight or overweight, the pouch is automatically diverted to a reject bin. The verified pouches proceed to the cartoning area. Here, a carton erector unfolds flat cardboard blanks and seals the bottom flaps with hot melt adhesive. Thus, open cartons are then conveyed to an indexing station, where robotic arms pick the filled pouches using vacuum grippers. These robots operate with vision guidance, ensuring the pouches are oriented correctly before placement. Each carton receives a set number of pouches, after which the top flaps are closed and sealed. Cartons then travel to the case packing area. Another robotic system groups the cartons into layers and places them into corrugated shipping cases. Each case is automatically labeled with barcodes and stacking instructions. Finally, the loaded cases are conveyed to the palletizing cell. Here, a 6-axis robotic arm equipped with suction cups lifts each case and arranges them on a wooden pallet in a tightly packed configuration. The completed pallet is wrapped with a stretch film using a rotating arm wrapper. This layer of plastic holds the cases together for transport, protecting them from moisture and movement. The entire pallet is then scanned for load integrity before being conveyed to the staging area, awaiting dispatch to distribution centers. All this activity is coordinated by a central manufacturing execution system. The MS tracks every movement and status of the materials, from peanut intake to finished carton. It interfaces with programmable logic controllers on the production floor to dynamically adjust machine settings based on real-time feedback. For example, if a slight shift in chocolate viscosity is detected, the MES can command the tempering unit to fine-tune the temperature curve. Similarly, if the peanut butter depositor records a higher than average flow rate, the filling head's piston stroke is automatically adjusted to compensate. Material traceability is ensured by RFID tagged ingredient containers, and barcode-scanned intermediate products. This allows every peanut butter cup mini to be traced back to the exact raw material batch it came from. Sensors track humidity and temperature at every stage, particularly within the cooling tunnels and storage silos. Even foil wrappers are logged and matched with machine lot codes. Automation is layered at every level. Pick-and-place robots replace manual handling. Vision systems eliminate the need for human inspection. Real-time analytics optimize yield and reduce waste. Redundant systems ensure that any malfunction is isolated without halting the entire line. Conveyor speeds are synchronized across zones to maintain timing continuity. The packaging line continues with precise, timed coordination as the sealed cartons are conveyed toward the aggregation system. This system groups multiple cartons into defined sets according to the final pallet configuration. A servo-controlled diverter arm separates cartons into staging lanes. Once the predefined group is complete, often in rows of 6, 8, or 12, an overhead gantry equipped with vacuum suction heads lowers onto the group, lifts the entire set, and places it into a corrugated master case. This movement is completed in a single fluid action to minimize cycle time. Before the master case is sealed, a leaflet or folded instruction insert, used for some international markets, is dropped into the case by a pneumatic feeder. The flaps of the case are then closed and sealed with twin hot melt glue nozzles, precisely depositing adhesive in a consistent bead along the contact edges. Immediately after the flaps are compressed shut, a set of pressure rollers moves over the top of the case to ensure uniform adhesion. Next, the sealed master case is conveyed under an inline labeling system. Here, a thermal transfer printer produces large format labels containing product SKUs, batch codes, barcodes, and destination identifiers. An applicator arm synchronizes with the moving case, slapping the printed label onto the side panel without stopping the line. A high-resolution camera follows, verifying that each label is present, legible, and properly aligned. If the label is missing or unreadable, the case is automatically diverted into a correction lane where a manual relabeling station awaits. From there, the master cases move toward the palletizing station. Palletizing begins with empty wooden pallets being fed from a stacker. An automatic destacker lowers and releases a pallet onto the loading zone. A vision-guided robotic arm reads the barcodes on incoming cases to determine their orientation and designated location on the pallet. Each case is picked up with a vacuum gripper or clamp-style end effector and rotated, if necessary, to match the programmed stacking pattern. Cases are placed in interlocked layers, alternating orientation by row to increase structural stability. As each layer is completed, a slip sheet is dispensed from a vertical magazine and dropped onto the layer before the next row begins. This adds friction between layers and protects the contents from compression. When the pallet reaches its full load height, typically 6 to 8 layers, the robotic arm disengages, and the loaded pallet is conveyed to the wrapping station. At the wrapping station, the pallet is rotated on a turntable while a film carriage ascends and descends, dispensing stretch film under tension. The film is pre-stretched using powered rollers to increase load stability without using excess material. Once wrapping is complete, the film is cut and sealed using a heat blade, and a final top sheet of film is applied to provide dust and moisture protection. A cornerboard dispenser may apply vertical reinforcements along the pallet edges if required for export shipping. After wrapping, each pallet is routed through a check-in station equipped with RFID scanners and weight sensors. The data collected here is sent to the factory's logistics system, which assigns the pallet a dock number and dispatch order. Automated guided vehicles or laser-guided forklifts transport the pallet from the end of the line to the designated outbound dock. This end-of-line logistics system integrates seamlessly with upstream production data allowing full visibility and traceability from raw ingredients to finished pallet. The factory's architecture is designed for just-in-time flow, meaning there is minimal buffer storage between stages. The speed and precision of every downstream step are tightly dependent on the upstream processes delivering product at the correct pace. Meanwhile, upstream processes like ingredient blending and chocolate tempering continue in a closed loop. The chocolate mass in the tempering unit is constantly monitored by inline viscometers and refractometers. These instruments send live data to the automated control system, which modulates the heating and cooling stages to keep the chocolate in its stable crystalline form. Any deviation in viscosity or temperature is corrected in real time by adjusting the flow of chilled or heated glycol in the jacketed lines. The peanut butter filling line operates on a similar control philosophy. The filling's consistency is maintained within strict tolerances using shear rate sensors and pressure transducers embedded in the deposit line. If a slight thickening is detected, a micro amount of vegetable oil is introduced upstream at the blending tank, rebalancing the emulsion. These corrections are automated and occur without interrupting production. To ensure continuous supply, the system uses dual tanks for both chocolate and peanut butter. While one tank feeds the depositor, the second is cleaned, refilled, or brought up to processing temperature. This tank switching sequence is managed by a series of automated valves and level sensors. When the active tank nears depletion, the system seamlessly switches to the secondary tank, ensuring an uninterrupted flow to the depositor heads. The mold handling system is another key area of automation. Molds are part of a closed-loop carousel that runs on synchronized drives and encoders. Each mold is equipped with an RFID chip embedded in its frame. This allows the system to track the position and status of every individual mold, whether it is empty, partially filled, cooling, or at the demolding stage. If any mold is flagged as defective, it is automatically diverted to a cleaning and inspection loop where high-pressure water jets and ultrasonic baths clean the mold before it re-enters production. The cleaning systems themselves operate on fixed intervals. Chocolate contact lines are flushed with a food-safe solvent followed by hot water, then dried with filtered air. The peanut butter system undergoes a similar process, but also includes pigging, a technique where a cylindrical plug is pushed through the pipe to scrape residual filling. This ensures complete evacuation of material between batches and prevents buildup that could interfere with flow or hygiene. Another critical area is temperature management. Chocolate, peanut butter, and the air in various tunnels must be tightly controlled. The cooling tunnels operate with precision climate control using chilled glycol coils and air recirculation fans. The air inside each tunnel is filtered and dried to prevent condensation from forming on the cooling surfaces. Each tunnel is divided into zones, and the temperature in each is independently adjustable. This allows the product to be gradually cooled in stages, minimizing thermal shock and maintaining product integrity. The wrapping foil is also treated as a critical input. Foil rolls are stored in a humidity-controlled chamber and automatically loaded into the wrapping machines by robotic arms. Before entering the wrapping system, each roll is scanned with a spectrometer to verify that the foil's thickness, reflectivity, and coating align with specifications. Foil with even slight variations in thickness can cause machine misfeeds or affect the aesthetic of the final wrap. Every component, from the ingredient to the final unit, is integrated into a massive data collection system. Thousands of sensors measuring temperature, pressure, weight, viscosity, and speed generate real-time data that feeds into a plant-wide dashboard. This dashboard is monitored by a centralized control room that receives live alerts, trend reports, and predictive maintenance warnings. If a chocolate depositor starts running slightly slower than average, The system calculates whether this indicates wear on a motor, blockage in a pipe, or fluctuation in chocolate viscosity. A maintenance ticket is generated automatically, allowing for preemptive servicing before failure occurs. The same predictive logic applies to wear-prone parts like the foil wrapping mandrels, depositor pistons, or vacuum grippers. Cycle counts are tracked, and components are retired or serviced according to usage thresholds. This predictive maintenance ensures that the machines run at optimal efficiency with minimal unplanned downtime. Air quality within the production zone is also tightly regulated. The environment is filtered using HEPA-level air handling units that remove particulates and microorganisms. Positive pressure is maintained in clean zones to prevent contamination from adjacent areas. Even the flow of personnel and carts is controlled via airlock-style entry points and floor-level pressure mats that trigger sanitation protocols. The factory operates in a rhythm of continuous throughput. Each component, chocolate mass, peanut butter filling, molds, wrappers, pouches, cartons, pallets, flows through its respective subsystem at precisely regulated speed. The coordination of these movements relies not only on mechanical timing, but also on software orchestration. The entire plant is governed by a hierarchy of control. Field-level PLCs manage individual machines, line controllers handle sequences of machines, and supervisory control software integrates everything into a single process flow. Lindt chocolate is produced in a tightly structured factory process that begins with the transformation of raw cocoa beans into ultra-fine, smooth, and creamy chocolate using specialized machines, proprietary techniques, and finely tuned timing sequences that preserve the delicate flavors of cocoa while eliminating bitterness and grit. The process begins when whole dried cocoa beans arrive at the factory in large bulk containers and are conveyed directly into storage silos built to maintain low humidity and a stable temperature to prevent any premature oxidation or moisture absorption. From these silos, the beans are measured out by weight and directed into a cleaning unit where vibrating screens, air classifiers, and magnetic separators remove stones, dust, string, and any foreign matter so that only clean beans proceed to the next step. The cleaned cocoa beans are then transferred to a batch roaster or continuous drum roaster, which exposes them to dry hot air with precise temperature control and rotation speed to ensure the beans are heated evenly from all sides. Roasting develops the flavor of the cocoa, reduces astringency, and darkens the color of the nibs inside the shell. The temperature and duration of roasting are carefully controlled depending on the variety and origin of the bean, and are adjusted based on moisture content and desired flavor profile. Once roasted, the beans are cooled rapidly using forced air to prevent over-roasting, and then they move to the winnowing machine. The winnowing process cracks each roasted bean and separates the outer shell from the nibs inside. This is done using mechanical rollers that crush the beans gently, and blowers that blow away the lighter shells while heavier nibs fall into collection bins. The winnowed nibs are what contain the cocoa solids and cocoa butter required for chocolate production. These nibs are directed into large grinding chambers where rotating steel drums or stone rollers crush them into a thick, dark, gritty paste known as cocoa liquor. This liquor is then pumped into a series of high-pressure hydraulic presses that separate the fat from the solids. The fat becomes cocoa butter, while the remaining cake is pulverized into cocoa powder. In parallel, whole milk powder, sugar, and additional cocoa butter are stored in bulk hoppers and prepared to be added to the chocolate base. The exact formulation depends on whether the chocolate being made is milk, dark, or white. For milk chocolate, cocoa liquor is blended with sugar, milk powder, and cocoa butter in large horizontal mixers until a uniform paste forms. This coarse chocolate mass is then sent to the refining stage. Refining involves passing the chocolate paste through a sequence of steel rollers that reduce particle size. Each roller set progressively narrows the gap, crushing sugar crystals and milk particles until they are reduced to between 15 and 20 microns. This ultra-fine particle size is critical for the mouthfeel of Lindt chocolate, ensuring there is no graininess when the chocolate melts on the tongue. The refined chocolate then moves to the conching stage, which is one of the defining steps in Lindt production. Conching is done in elongated mixers called conches that slowly knead the chocolate at elevated temperatures, typically between 45 and 80 degrees Celsius, for several hours or even days, depending on the recipe. The purpose of conching is to develop flavor and texture. During this phase, volatile acids and off flavors are driven off by heat and agitation, while the friction created by the mixing reduces viscosity and smooths the fat dispersion. This stage also transforms the aroma profile, eliminating any lingering bitterness or sharp notes and rounding out the flavor. In Lindt's process, conching is considered both a science and an art, and the parameters are adjusted delicately to reflect the cocoa origin, sugar type, and desired smoothness. Once the chocolate mass has reached the optimal flavor and flow characteristics, it is transferred to tempering machines. Tempering is a controlled heating and cooling cycle that aligns the cocoa butter crystals into a stable form, known as Form Vi. This ensures that the finished chocolate will have a glossy finish, a crisp snap, and will not develop bloom or grayish streaks over time. In the tempering machine, the chocolate is first heated above the melting point of all cocoa butter crystals, then cooled to a point where only Form 5 can reform, and finally reheated slightly to working temperature. During this process, precise control of temperature and agitation is vital. Tempered chocolate is now ready for molding or enrobing. For bar production, tempered chocolate is poured into polycarbonate molds, which are vibrated on automated shakers to remove air bubbles and allow the chocolate to settle evenly into every corner. The molds are then passed through cooling tunnels, where cold air gradually lowers the chocolate temperature until it sets and solidifies. For filled chocolates or truffles, the molds may first receive a thin shell of chocolate, which is cooled and then filled with soft centers like ganache, praline, or liqueur before being sealed with more chocolate and cooled again. Once the chocolate has solidified, the molds are inverted and gently flexed by mechanical arms or vibration plates to release the bars or pieces. These are conveyed through a final inspection area where high-speed cameras and vision systems scan for imperfections such as broken corners, air pockets, or deformed logos. Defective. Pieces are rejected automatically, and perfect pieces proceed to wrapping. Wrapping is tailored to the product type. Lindt bars are typically wrapped in foil, followed by an outer paper sleeve. Machines cut foil to precise dimensions, fold it tightly around each bar, and then apply the paper wrapper using hot glue or pressure-sensitive rollers. Filled chocolates and balls are often wrapped in twisted foil ends or sealed flow packs using high-speed rotary packaging machines. Each wrapped unit is date-coded and batch-labeled for traceability. The wrapped chocolates are grouped into cartons by robotic arms that use suction cups to pick and place items into retail display boxes or shipping trays. Cartons are sealed, labeled, and palletized on automated stations where stretch wrap secures the load for transport. Pallets are scanned, assigned barcodes, and stored in climate-controlled warehouses to preserve flavor and appearance. The ambient temperature is maintained between 15 and 18 degrees Celsius with low humidity to prevent sugar or fat bloom from forming. Throughout the entire process, every parameter, from roast temperature to conche duration to tempering curve, is logged and monitored by a central control system. Inline sensors track viscosity, temperature, and particle size, while samples are pulled regularly for lab testing. These lab tests include moisture content, flow behavior, flavor analysis, and crystal structure confirmation to ensure the chocolate meets Lindt's quality standards. Chocolatiers also perform sensory evaluations, tasting samples for balance, aroma, melt, and finish. Hygiene and cleaning are equally critical in the production line. Chocolate making equipment is cleaned between product changes using melted cocoa butter flushes, which push out remnants of previous batches, followed by food-grade detergent cycles and high-pressure rinse systems. All cleaning is validated with swabs and lab tests to prevent flavor, cross-contamination, and microbial growth. In factories producing multiple chocolate types, changeovers are scheduled with precision to minimize downtime. Dark chocolate lines are usually run first, followed by milk, and then white chocolate, since darker varieties are more difficult to flush from equipment. Any chocolate not meeting specification during changeover is reworked or diverted to non-retail uses. Each ingredient in Lindt chocolate is treated with care. Sugar is milled to uniform crystal size and stored in dry silos with dehumidifiers. Milk powder is kept in oxygen barrier bags to preserve freshness. Cocoa butter is melted and filtered through fine mesh screens to remove impurities before blending. Even inclusions like nuts or fruit are roasted or candied on site to preserve their crunch and freshness. And they're added via gravity feeders that deposit precise amounts into the mold as chocolate flows in. The finished product that arrives on shelves results from a careful sequence where every gram of chocolate has passed through dozens of machines, heat cycles, mixing steps, and quality gates to guarantee it matches Lindt's profile for shine, snap, aroma, and flavor. From bean to bar, the chocolate moves with purpose through a network of conveyors, tanks, rollers, pumps, sensors, and skilled calibration, ensuring that what ends up in the foil wrapper is not just chocolate, but a refined and deliberate experience. Hershey's chocolate is manufactured through a large-scale factory process that transforms raw agricultural ingredients into solid molded chocolate bars, using a continuous sequence of heating mixing, refining conching, tempering molding, and packaging that is engineered for consistency, scale, and shelf life. The process begins with the intake of whole, dried fermented cocoa beans that are sourced in bulk and delivered in freight containers to the processing facility, where they are offloaded using vacuum conveyors or bulk tipping systems into steel silos designed for moisture protection and temperature stabilization, so the beans are kept in ideal condition before production begins. From these silos, the beans are moved into a cleaning station where mechanical sieves, air separators, and magnetic traps remove foreign matter such as twigs, dust stones, and bits of string. And the cleaned beans then enter large batch roasters or continuous flow roasting drums where hot air is circulated through the rotating chamber to heat the beans evenly and activate the chemical changes responsible for chocolate flavor and aroma. The exact roasting temperature and time are carefully controlled to vary the flavor strength depending on the blend being produced, and the roasted beans are then cooled quickly using forced air or vacuum systems to lock in the desired profile and prevent overdevelopment. Next, the cooled roasted beans pass through a cracking and winnowing machine where roller blades break the shells apart, and airflow systems separate the lighter papery husks from the heavier cocoa nibs, which contain the actual cocoa solids and cocoa butter required for chocolate production. The separated nibs are collected and sent to grinding chambers, where heavy granite rollers or steel grinders crush them into a thick, dark paste known as chocolate liquor, which is not alcoholic, but simply refers to the pure ground state of cocoa solids suspended in their own fat. At this stage, the chocolate liquor is held in heated storage tanks, where it can be separated into cocoa butter and cocoa solids if necessary, using hydraulic presses or used directly in chocolate mass formulation. The chocolate base used for Hershey's milk chocolate typically includes chocolate liquor, sugar milk, powder, cocoa butter, and sometimes emulsifiers to improve flow properties. And in this stage, these raw materials are measured precisely using load cells and volumetric dosing systems before being transferred into industrial blenders where they are mixed at high speeds into a coarse brown paste. The sugar crystals are still relatively large at this point, and the milk powder has not fully hydrated, so the mixture is lumpy and thick. But the goal of this step is to distribute the ingredients uniformly before refining. The refining process consists of passing the chocolate paste through a 5-roll mill or similar refining system, which crushes and shears the mixture repeatedly until all particles are reduced to between 15 and 20 microns in size, which is below the threshold of perception on the human tongue and is responsible for the smooth texture of finished chocolate. The refined powdery mass exits the rollers as dry flakes, which are collected and fed into large conching vessels, which are long horizontal mixers with heavy paddles that knead the chocolate continuously while applying gentle heat. Conching is one of the most important steps in the process and can last from several hours to a full day, depending on the batch size and the desired flavor characteristics. And during conching, the frictional heat softens the cocoa butter, allowing it to coat sugar and milk particles completely, while the mixing action evaporates unwanted volatile acids that contribute bitterness and also promotes chemical bonding between ingredients that gives chocolate its rounded flavor and creamy mouthfeel. In Hershey's process, this stage may include the addition of flavor compounds or the use of proprietary heating profiles that contribute to the distinctive, sweet, slightly tangy note associated with their milk chocolate. After conching, the now liquid chocolate mass is pumped through a fine mesh filter to remove any remaining solids and then enters the tempering system, which is a temperature-controlled series of heat exchangers and holding tanks that bring the chocolate through a controlled heating and cooling cycle designed to stabilize the cocoa butter crystals into the desired form V structure, which provides gloss snap and resistance to fat bloom. The tempering process requires careful monitoring of viscosity temperature, shear rate, and time to produce a chocolate that will remain stable during storage and distribution. Once tempered, the chocolate is moved into the molding line where it is dispensed into bar molds, using precise portioning heads that fill each cavity to the exact weight required. And the filled molds are shaken on vibrating tables to eliminate air bubbles and ensure even distribution of the chocolate across the mold. The molds then pass through a cooling tunnel where refrigerated air is circulated in stages to gradually bring the chocolate down to the release temperature, allowing it to solidify without developing stress cracks or surface bloom. When the chocolate has fully set, the molds are inverted and the bars are ejected using mechanical arms or flexing systems that pop the finished bars onto conveyor belts for inspection. Every bar passes under a series of vision systems that scan for surface defects, broken edges, misaligned logos, or irregular thickness, and any bar that fails inspection is automatically diverted for rework. Acceptable bars move forward to the wrapping section, where high-speed machines fold foil or film around each piece and seal it using heat or pressure depending on the packaging format. Paper sleeves or cardboard cartons are then applied and printed with product information barcodes and expiration dates using inline inkjet or laser printers. Wrapped bars are grouped into shipping cases by robotic packing arms and loaded onto pallets, which are stretch wrapped and labeled for traceability before being moved into temperature-controlled storage rooms maintained between 15 and 20 degrees Celsius to preserve texture and flavor. From this point, the bars are distributed through refrigerated trucks or ambient carriers depending on shelf life and destination requirements. In parallel with production, the entire process is monitored by sensors that record key data at every stage, from ingredient weight and tank temperature to roller pressure and mold cavity fill speed. And this data is fed into a centralized quality control platform that logs all production variables and triggers alerts if any parameter drifts outside the approved range. Quality assurance teams sample bars from each batch and test them in laboratories for moisture content, melt profile, flavor, strength, hardness, and microbiological stability. And these tests ensure that every bar maintains the same quality level regardless of where or when it is produced. All equipment used in the chocolate production line is constructed from food-grade stainless steel and is subject to strict sanitation protocols between product runs. Clean-in-place systems flush liquid chocolate from pipes and tanks using melted cocoa butter, followed by hot detergent solutions and sterile water rinses. And these cleaning cycles are verified using swab tests and microbial analysis before the next production run begins. During cleaning, mechanical components such as belts, pumps, and seals are inspected for wear and lubricated with food-safe oils to maintain performance and prevent contamination. Because Hershey produces multiple chocolate types, including dark white and flavored variants, the factory must perform regular changeovers that are scheduled with precision to minimize waste and avoid flavor crossover. And this is typically done by running from the lightest product to the darkest, so that any residual ingredients are less likely to impact flavor in the next batch. Storage of ingredients is just as critical as processing, and milk powder is kept in dehumidified silos lined with oxygen barriers, while cocoa butter is stored in heated jacketed tanks that maintain a constant liquid state, and sugar is held in dry bins fitted with vibratory feeders to ensure consistent flow into the mixers. Even inclusions like almond toffee or cookie pieces are added through dedicated feeders designed to introduce solids at the molding stage without disrupting flow or causing jams. From beginning to end, Hershey's chocolate production line is a finely tuned balance of mechanical engineering, food science, and sensory evaluation, where the transformation of beans into bars depends on maintaining strict control over texture, flavor, and structural integrity. The iconic bars that result are the outcome of thermal history, particle refinement, fat crystallization, and packaging precision that together produce a chocolate that is consistent across millions of units and recognized by consumers around the world. Godiva chocolate production begins with the careful handling of raw cocoa beans, which arrive at the factory in bulk loads from cocoa growing regions and are stored in cool, dry silos that prevent moisture contamination, oxidation, and pest activity. These beans are first cleaned through mechanical sifters that remove stone shells, dust, and organic debris using a series of vibrating screens, suction fans, and magnetic traps. Once cleaned, the beans are weighed and portioned by automated systems and conveyed to the roasting chambers, which are precision-engineered rotating drums capable of uniform thermal penetration across the entire mass of cocoa beans. Roasting is the first flavor-developing stage in the chocolate-making process, and in the Godiva production method, it is carried out at moderate temperatures for extended periods, which helps preserve the aromatic volatiles while driving off unwanted acidity and bitterness. Each batch is roasted based on its origin and moisture level, with constant temperature regulation using internal thermocouples that feed data to a computerized control system. Once the beans are fully roasted, they are immediately cooled with forced air systems that halt the roasting curve and stabilize the volatile compounds formed during heating. The next step is winnowing, which involves cracking the roasted beans open to separate the brittle shells from the cocoa nibs inside. The beans pass through a mechanical cracker that gently fractures them, and a pneumatic winnower that blows the lighter shells away while the heavier nibs fall into collection bins. These nibs are the core ingredient in all chocolate and contain both cocoa solids and cocoa butter in their natural ratio. The nibs are routed to a pre-grinding unit where rotating stone rollers or steel discs crush them into a thick, gritty paste known as cocoa liquor. This liquor is heated slightly to reduce viscosity and then transferred to high-pressure hydraulic presses that squeeze out the cocoa butter, leaving behind a dense cake of compressed solids which are ground into cocoa powder. For milk chocolate production, the cocoa liquor is blended with refined sugar, high-quality milk powder, additional cocoa butter, and in some recipes, a hint of vanilla or lecithin, which acts as an emulsifier. Each ingredient is dosed using gravimetric feeders and poured into large, high-speed mixers where they are combined into a smooth, uniform brown paste. This initial chocolate mass is far too coarse to be palatable, so it is sent to the refining system. This consists of a 5-roll mill where the mixture passes between sets of rollers that progressively reduce the particle size down to below 20 microns, creating a texture that feels smooth and creamy on the tongue. After refining, the powdered chocolate mass is transferred into conching machines, which are large horizontal vessels with internal mixing blades that work the chocolate slowly while applying gentle heat. This process can take anywhere from 12 to 24 hours, depending on the desired flavor profile, and is critical for developing the smooth texture, deep aroma, and balanced flavor that distinguishes Godiva from other mass-market chocolates. The conching action evaporates undesirable acids and moisture while distributing the cocoa butter evenly over every particle, which contributes to the distinctive mouthfeel and melt of the final product. Once conching is complete, the chocolate is sent through a filtration unit to remove any remaining impurities and then proceeds to the tempering stage, which is one of the most technically precise parts of the entire process. Tempering involves heating the chocolate to above its melting point, then cooling it down to initiate the formation of stable cocoa butter crystals known as Form 5, and then slightly reheating it to a working temperature, where those crystals can be maintained in suspension. This controlled crystallization ensures that the finished chocolate will have a glossy sheen, a crisp snap when broken, and a long shelf life without the development of sugar or fat bloom. The entire tempering process is carried out in enclosed stainless steel tanks equipped with agitators and digital thermostats that keep the temperature profile exactly within a 1-degree tolerance. The tempered chocolate is now ready for molding or enrobing. For solid chocolate bars or shapes, the tempered chocolate is poured into precision-engineered molds made of food-grade polycarbonate. These molds are vibrated to remove air bubbles and ensure that the chocolate spreads evenly into every corner and detail of the design. The filled molds then pass through a cooling tunnel that gradually lowers the temperature, allowing the chocolate to solidify and contract slightly so it can release cleanly from the mold. The pieces are then turned out and conveyed to the packaging line. For filled chocolates like pralines, truffles, and caramels, the process adds additional steps. The mold is first coated with a thin layer of tempered chocolate using spinning or tilting mechanisms to create a uniform shell. This shell is cooled just enough to firm up and then filled with liquid centers like ganache hazelnut paste or fruit cream using precision nozzles that deliver exact volumes to each cavity. Once filled, the chocolates are sealed with a final layer of chocolate and sent through a second cooling tunnel to solidify completely. These filled chocolates are then demolded and sent to wrapping. Enrobed chocolates, such as chocolate-covered nuts or biscuits, are passed on a conveyor belt under a waterfall of tempered chocolate where they are coated completely and pass under a vibrating plate that ensures even coverage and allows excess chocolate to drip off. The enrobed pieces then pass through a cooling tunnel similar to the molded chocolates where the coating solidifies uniformly. Wrapping is carried out using high-speed automated systems that use foil or flow wrap depending on the product. Each chocolate is first wrapped in an inner layer to preserve freshness and then given an outer wrap or box depending on whether it's a single piece or part of a collection. These wrappers are applied using thermal sealers and folded precisely by mechanical arms to maintain presentation quality. The finished chocolates are grouped into assortments using pick-and-place robots that load them into rigid trays or decorative boxes, which are then closed, labeled, and shrink-wrapped for transport. Throughout the entire production process, quality control is integrated into every stage. Inline sensors measure parameters like particle size, viscosity temperature, and moisture content. Random samples are taken and tested for flavor consistency, flow behavior, microbiological safety, and visual appearance. Each batch is tracked from bean to box using barcode systems and digital batch records, which allow full traceability and accountability. Any deviation from the strict specifications results in automatic rejection and investigation to maintain the high quality associated with Godiva. Packaging lines are designed not only for speed, but also for delicate handling. Chocolates are not simply dropped into boxes, but placed gently by grippers or vacuum arms to prevent any scuffing or deformation. Seasonal and limited edition boxes are assembled by dedicated packaging stations that include decorative inserts, gold leafing, or ribbon application, all of which are coordinated with the central production database to match inventory with demand forecasts. Finished products are palletized automatically and moved to cold storage areas where the ambient temperature is held between 15 and 18 degrees Celsius with low humidity to protect against fat bloom sugar crystallization or flavor degradation. Logistics systems monitor inventory in real time and coordinate dispatch using climate-controlled vehicles that ensure the chocolates arrive at retail destinations in pristine condition. Factory sanitation is handled with clean-in-place systems for all enclosed equipment and rigorous manual cleaning protocols for all external surfaces. Between product types, especially when transitioning from dark to milk or white chocolate lines, are flushed with cocoa butter and inspected using allergen tests to confirm no cross-contamination occurs. Equipment such as molds tempering tanks and piping is made from food-grade stainless steel and is subject to frequent validation, including swab tests, microbiological plating, and ATP analysis. Each product that leaves the factory reflects a meticulously controlled combination of mechanical design, sensory expertise, thermal precision, and ingredient handling, all executed on a scale that allows handcrafted quality to meet global demand. Godiva's reputation depends on this balance, where artistry meets automation, where every bar and truffle is not only shaped by steel and steam, but guided by formulas and feedback that ensure every box offers the same refined, luxurious experience no matter where it is opened. Chocolate chip cookies are manufactured by building a controlled dough system, portioning it into uniform pieces, baking to a defined moisture gradient, then cooling and packaging to preserve crispness or softness depending on the target style. Production starts with ingredient conditioning because dough behavior depends on temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is managed as two streams when both granulated sugar and brown sugar are used. Granulated sugar is screened for consistent crystal size. Brown sugar is broken down to remove hard clods because clods create dark pockets and uneven spread. Fats are conditioned to a plastic state so they cream smoothly and do not separate. Eggs or liquid egg products are tempered to a consistent temperature so they emulsify predictably. Chocolate chips are stored cool so they keep shape during mixing and do not smear into the dough. The mixing sequence begins with creaming because it sets the cookie structure. Fat and sugar enter a mixer with a paddle tool that shears and folds. Creaming disperses sugar crystals through fat and traps small air cells. The amount of trapped air influences cookie lift and interior texture. Mixing time is controlled, so air incorporation stays consistent. Over-creaming yields excessive spread variation and fragile cookies. Under-creaming yields dense cookies with limited rise. If the formula uses brown sugar, its molasses content changes water binding and dough viscosity. Brown sugar is added early in creaming, so it breaks down and disperses. The ratio of brown to white sugar controls spread and chew because molasses holds moisture and affects browning. Salt and leavening can be added during creaming, so they distribute evenly. Leavening selection matters because baking soda promotes spread and browning, while baking powder adds lift. Eggs are added next to build an emulsion and hydrate proteins. Eggs are introduced gradually so the fat phase does not break. The mixer runs at a speed that maintains a stable emulsion. If eggs are dumped in too fast, the mixture curdles and the dough becomes inconsistent. Vanilla and other flavors are added with the egg stream because they disperse well in the liquid phase. Dry ingredients enter after the fat and egg system is stable. Flour is added in controlled increments to avoid dust and to prevent dry pockets. Mixing energy is reduced during flour addition because gluten development must be limited. Too much gluten makes cookies tough and reduces spread. The endpoint is a cohesive dough where flour is hydrated but the structure remains short due to fat coating. If the recipe includes starches or milk powders, they enter with the flour. Starch can soften texture by reducing gluten strength. Milk powders can increase browning and add dairy notes. Each addition changes water demand. Water demand is managed by egg level and by added water if used. Dough temperature is tracked because warm dough spreads more in the oven. Chocolate chips are added at the end of mixing to preserve chip integrity. Chips are folded in at low speed so they distribute without breaking. Distribution uniformity matters because each cookie needs a consistent chip count. Mixing after chip addition is kept short to avoid smearing chocolate into streaks. If chips are warm, they can melt and create muddy color. Chip temperature control prevents that. Once mixed, the dough often goes through a short rest. Rest allows flour hydration to complete and lets the dough firm as fats stabilize. Rest also reduces stickiness and improves portioning accuracy. Dough can be held in a cooled hopper to maintain a consistent temperature band. Consistent temperature is critical because it affects extrusion rate and cookie spread. Portioning converts bulk dough into individual pieces with defined mass. High volume lines use wire cut or rotary molded or depositor systems. Wire cut systems extrude a dough log through a die, and a moving wire slices portions. Die shape sets cookie diameter. Wire timing sets piece weight. Rotary mold systems press dough into engraved rollers that form shaped pieces. Depositors drop measured dollops for soft-style cookies. Each method relies on stable dough viscosity. During portioning, the dough is placed onto baking trays or oven bands. Spacing is controlled because cookies spread during baking. If pieces are too close, they merge. Spacing is managed by indexing belts and by tray loading patterns. Weight checks verify portioning accuracy because mass affects bake time and moisture. Baking is a staged heat process that sets shape and creates the desired texture. Cookies enter a tunnel oven with multiple zones. Early zones apply heat that melts fats and starts spread. As spread occurs, the cookie surface begins to set. Leavening gases expand and create internal porosity. Steam is generated from water in the dough and it contributes to lift. As baking continues, proteins coagulate and starch gelatinizes, then dries. These transitions transform dough into a solid matrix. Sugar dissolves in the early wet phase and then begins to recrystallize as moisture leaves. This sugar behavior affects crispness. The Maillard reaction and caramelization drive browning and flavor development. Oven temperature and airflow set the rate of these reactions. Texture is controlled by managing the moisture gradient. A crisp cookie is baked longer, so moisture drops low through most of the thickness. A chewy cookie is baked to leave more moisture in the center while the edges set. This requires careful control because the outer region can overbrown before the center hits target. Oven zones allow the line to drive strong, top heat early for structure, then moderate heat later for uniform drying. Airflow affects surface drying and color. High airflow removes moisture quickly and increases crispness. Lower airflow allows more moisture retention. Some ovens use impingement jets that drive heat into the surface rapidly. Others use convection with gentler airflow. The chosen profile is tuned to the dough formulation and piece size. Cookie spread is controlled by dough fat type and sugar ratio and dough temperature and early oven heat. If spread is excessive, cookies become thin and fragile. If spread is insufficient, cookies stay thick and can remain underbaked in the center. Lines adjust by changing dough temperature and by adjusting the first oven zone temperature. They can also adjust piece weight slightly to influence final diameter. When cookies exit the oven, they are fragile because the structure is still hot and fats are liquid. They move on to cooling conveyors that support them and prevent bending. Cooling must be controlled because rapid cooling can create cracking in crisp products. Gradual cooling allows structure to set as fats crystallize. Cooling also allows moisture to redistribute slightly within the cookie. This redistribution affects final texture. A cookie that feels soft when hot can become crisp after cooling as moisture equilibrates. For soft cookie styles, the process may include a rapid cooling step that limits moisture loss. For crisp styles, the process may include extended cooling with dehumidified air to drive moisture lower. Air humidity control matters because cookies can absorb moisture from humid air and lose crispness. Cooling tunnels therefore often use conditioned air. After cooling, the cookies may be inspected and sorted. Vision systems can reject merged cookies and broken cookies, and off-color pieces. Metal detection can be placed after cooling to protect final product flow. Sorting also aligns cookies for packaging and removes crumbs that would contaminate seals. Packaging is designed around moisture control because cookie texture is moisture sensitive. Crisp cookies require high barrier film that prevents water vapor ingress. Soft cookies require packaging that limits moisture loss so they do not dry out. Many lines use flow wrappers that seal each cookie or stacks of cookies. Film is formed around the product and sealed longitudinally and at the ends. Seal integrity is critical because small leaks change texture over time. If cookies are packed in trays, the trays protect against breakage. Cookies are loaded into plastic trays by robotic pick and place or by lane collators. Trays are then wrapped in film. Trays also control headspace and reduce movement that generates crumbs. For bagged formats, cookies are collated into stacks and then dropped into bags. Stack height and alignment are controlled so the bag seals cleanly. Biscuits are manufactured by converting flour, fat, sugar, and leavening into a stable dough, shaping that dough into uniform pieces, baking to a defined moisture endpoint, then cooling and packaging to preserve texture. Production starts with flour handling because flour properties control dough strength and spread. Flour is delivered in bulk and routed through sieves that remove lumps and foreign particles. Aeration during sieving improves consistent hydration. Flour temperature and moisture are monitored because they affect water demand. If flour is warm, the dough softens and smears in sheeting. If flour is cold, the dough can crack and resist forming. The line, therefore, conditions flour to a narrow temperature range before mixing. Sugar is prepared based on biscuit style. Granulated sugar is screened to control crystal size and reduce dust. Powdered sugar is delumped because hard clods create white streaks. Brown sugar is broken down and evenly distributed because molasses pockets create dark spots. Salt is weighed and kept dry so it flows consistently into feeders. Leavening agents are staged separately because their particle size and reactivity affect lift. Fats are tempered to a plastic consistency so they disperse evenly and limit gluten development. Water and liquids are prepared with controlled temperature. Water temperature is used as a mixing control lever. Warmer water speeds hydration and shortens mixing time. Cooler water firms dough and improves machining. Syrups and dairy liquids are held in jacketed tanks if used. Liquid egg or milk can be included for richer biscuits, and it is tempered to avoid curdling in the fat phase. Mixing begins with a sequence selected to manage gluten. For short, crisp biscuits, the process aims to limit gluten formation. Fat is combined with flour early to coat flour particles. This coating reduces water access and reduces gluten development. Mixing equipment uses paddles or sigma blades that fold and smear fat into flour without overworking. Sugar and salt can be added at this stage, so they distribute through the fat-coated flour. Water is then added gradually while mixing continues at controlled speed. The aim is to hydrate enough to form a cohesive dough while keeping it short. Overmixing develops gluten and makes biscuits tough. Undermixing leaves dry pockets that tear during sheeting. The mixing endpoint is judged by dough uniformity and by torque and by visual cohesion. For semi-sweet biscuits or cookies, the line may use a creaming step. Fat and sugar are creamed to incorporate air and create a lighter structure. Liquids are then added to form an emulsion. Flour is added last and mixed briefly. This method yields more spread and a different crumb structure. Both methods rely on controlling dough temperature and mixing energy. After mixing the dough often enters a rest stage. Rest allows moisture to distribute through flour particles. Rest also lets the dough relax and reduces elastic snapback. Reduced snapback is important for precise cutting and consistent size. Rest temperature is controlled because warm rest softens fat and changes dough stiffness. The dough then moves to forming, which can be sheeting, extrusion, or molding. Sheeting is common for many biscuits. Dough passes through reduction rollers that gradually decrease thickness. Multiple passes avoid tearing and keep texture uniform. Gauge rollers set the final thickness. Thickness control is crucial because it sets bake time and final moisture. Dusting flour can be applied during sheeting to prevent sticking. Dusting must be minimal because excess dust burns and creates bitter specks. The line uses controlled dusting and brushes to remove excess. Dough temperature is controlled during sheeting because warm dough sticks and cold dough cracks. After sheeting, the dough is cut into shapes. Rotary cutters punch biscuits from the R sheet. Cutter dies define shape and size. Scrap dough is lifted away and recycled. Scrap handling is controlled because repeated recycling can toughen dough by building gluten. Many lines limit scrap ratio by controlling sheet width and cutter layout. Docking is often used for flat biscuits. Docking pins punch small holes in each piece. Holes allow steam to escape during baking. This prevents blistering and ensures flatness. Docking pattern influences surface appearance and break strength. The docking station is synchronized with cutter speed, so holes stay centered. For molded biscuits, a rotary molder can be used. Dough is pressed into engraved cavities on a roller and then released onto a conveyor. This method creates surface patterns and can handle softer dough. Release depends on dough fat level and temperature. If dough is too warm, it smears in cavities. If too cold, it cracks and does not fill details. Extrusion can be used for certain biscuit forms. Dough is forced through a die to create a continuous rope. The rope is cut into segments or shaped further. Extrusion requires dough with consistent viscosity. Viscosity is controlled by water level and fat plasticity. Formed pieces are transferred onto baking bands or trays. Transfer must avoid deformation. Conveyors use gentle acceleration and minimal drop heights. Spacing is controlled because pieces can spread or expand slightly during baking. If pieces are too close, they can merge. Baking is the main transformation stage. Biscuits enter a tunnel oven with multiple heat zones. Early zones apply heat that sets surface structure. Fat melts and the dough begins to relax. Water begins to evaporate and steam forms within the piece. Leavening reacts and produces gas that creates internal porosity. As baking continues, starch gelatinizes, then dries into a rigid matrix. Proteins coagulate and contribute to structure. Sugar dissolves in the early wet phase and then participates in browning reactions as moisture falls. Maillard reactions and caramelization develop color and flavor. Oven temperature and airflow control the rate of these reactions. Moisture endpoint is a primary target because it defines crispness and shelf stability. For crisp biscuits, the line drives moisture low so the biscuit fractures cleanly. For softer biscuits, the line stops earlier to retain more moisture. Moisture control is managed by oven profile and by piece thickness. A thicker biscuit needs longer bake or higher heat. A thinner biscuit can overbrown quickly if heat is too high. Airflow influences drying and surface texture. Strong convection removes moisture fast and yields a drier surface. Gentler airflow allows more, even internal drying. Many ovens use independent top and bottom heat control. Bottom heat drives structure set from the band side. Top heat drives surface color. Balancing top and bottom heat prevents warping and ensures even bake. Spread and shrink are managed through dough formulation and early oven conditions. If early heat is low, the dough can spread too much before setting. If early heat is high, the surface sets quickly and limits spread. The line adjusts the first oven zone to tune diameter and thickness. After baking the biscuits, exit hot and fragile. They move to cooling conveyors where they firm as fats, resolidify. Cooling also allows moisture to redistribute slightly. For crisp biscuits, cooling air is often dehumidified because biscuits can absorb moisture from humid air and lose snap. Cooling is staged, so thermal stress does not crack the biscuits. During cooling, the biscuits are inspected and sorted. Vision systems can detect overbaked color and broken pieces and misshapes. Metal detection can be placed after cooling. Crumb removal systems collect loose fragments that would contaminate packaging seals. If the product includes surface toppings such as sugar crystals or salt or glaze, the application is timed to surface condition. Sugar sanding is often applied before baking so crystals embed and partially melt. Glaze can be applied after baking and then dried lightly. These steps require separate dosing systems and add additional moisture management considerations. Packaging is designed to protect biscuits from moisture and breakage. Biscuits are collated into stacks and oriented. Stacking systems use lanes and pushers to form uniform packs. The packs are then flow wrapped or placed into trays. Flow wrapping uses barrier film that blocks water vapor. Tray packs provide mechanical support and reduce breakage during transport. Seals must be clean because crumbs can interfere with seal integrity. Packaging machines use crumb extraction near the seal jaws. Film tension and seal temperature and dwell time are controlled, so seals are tight. Coating is applied for traceability. Check weighers confirm count or weight. Oat bars are manufactured by converting oats and binders into a cohesive slab, setting that slab by baking or cooling, then cutting it, and packaging so texture and moisture stay within a tight window. Production starts with oat preparation because particle size distribution controls chew and structural strength. Rolled oats are screened to remove fines and oversized flakes. Fines create dust and can make bars dense and crumbly. Oversized flakes create weak points and poor cut edges. If the product uses oat flour or milled oats, that stream is prepared separately and sieved to prevent clumps. Nuts, seeds, or crisp inclusions are sized and cleaned so they do not introduce hard fragments that damage cutters. Sweetener and binder streams are prepared in parallel. Glucose syrup or similar syrups are held in jacketed tanks to maintain a stable viscosity for pumping. Sugar can be added as granulated crystals or dissolved into a syrup depending on the texture target. Fat sources, such as vegetable oil or butter, are melted and held at controlled temperature. If nut butters are used, they are warmed to a flowable state and mixed to eliminate oil separation. Emulsifiers can be staged to stabilize the binder and improve coating of dry particles. Dry minor ingredients are pre-blended to ensure uniform distribution. Salt is weighed and dispersed to prevent salty pockets. Leavening is used only in certain baked styles, and it is weighed precisely. Protein powders or milk powders are sieved because they form lumps when exposed to binder. Spices and flavors are blended into the dry premix or injected into the binder depending on volatility. The process creates a binder first because the binder must coat every dry particle quickly. A heated mixing kettle combines syrups and sugars and fats. Agitation keeps the mixture homogeneous and prevents hot spots. Temperature is raised to dissolve sugar if needed and to reach a target solids level. Solids level controls final stickiness and water activity. If solids are too low, the bars remain sticky and can weep. If solids are too high, the binder becomes glassy and the bar becomes hard. Cooking is used in many oat bar lines to adjust binder concentration. The binder is heated to drive off water and to raise viscosity. Time and temperature are controlled because overheating darkens sugars and changes flavor. When the binder reaches target viscosity, it is cooled slightly to a mixing temperature that will not damage heat-sensitive inclusions. Cooling also prevents excessive softening of oats during mixing. Flavor addition often occurs after this cooling step. Vanilla and spice extracts are injected, so aromatics are preserved. If fruit concentrates are used, they are blended in at controlled temperature because they can burn or separate when overheated. Acidulants can be added to balance sweetness and also to manage microbial stability. The binder is mixed until it is uniform and then it is pumped to the forming line. Dry blending begins with oats as the primary structural phase. Oats are loaded into a ribbon blender or a paddle mixer. The mixer runs at low speed to avoid breaking flakes. If nuts or seeds are included, they are added and distributed. Dry powders, such as protein, are added as a pre-mix to reduce streaks. The dry blend is mixed only until distribution is uniform because overmixing generates fines. Binder is then introduced into the dry blend. The binder is metered by mass flow, so the ratio remains stable. It is delivered through spray bars or a manifold that distributes it across the mixer width. The mixer switches to a folding action that turns the dry blend through the binder stream. The goal is rapid coating without crushing inclusions. Coating uniformity is critical because uncoated oats fall apart and overcoated zones become sticky clumps. Mixing endpoint is judged by appearance and by torque. The mass should look uniformly glossy with no dry pockets. It should flow as a cohesive mixture but still show discrete oat flakes. If the mass is too wet, it will smear during forming and create dense bars. If it is too dry, it will not bind and will shed crumbs during cutting. Temperature during mixing is monitored because warm mass flows better but can collapse structure later. Once mixed, the mass is transferred to a forming system that creates a continuous slab. Transfer chutes are designed to reduce segregation because heavier inclusions can settle. Many lines use a short transfer distance and a low drop height. The mass is fed onto a moving belt through a spreader that distributes it to full width. The spreader uses leveling bars and rotating paddles to create an even bed height. Compaction follows spreading and it defines bar density. A set of compression rollers presses the mass to a target thickness. Roller pressure and gap determine final thickness and porosity. Higher compression yields a dense bar with fewer voids and a cleaner cut. Lower compression yields a lighter bar with more chew and visible structure. Compression must be uniform across the belt to avoid thickness variation. If the product includes a base layer such as chocolate or yogurt coating, the sequence can include a bottoming step. A thin film is applied to the belt and partially set before the oat mass is deposited. This creates a bonded base that can act as a moisture barrier. The base layer thickness must be controlled because it affects cutting and packaging. Setting the slab depends on product style. For baked oat bars, the slab enters a tunnel oven. Baking drives off moisture and sets structure by solidifying sugars and fats. Oven zones are tuned to avoid overbrowning while reaching a target moisture endpoint. Airflow and temperature control surface drying and internal set. The slab must be firm enough to cut cleanly, but not so dry that it becomes brittle. For no bake oat bar setting is achieved by cooling rather than baking. The slab enters a cooling tunnel where fats crystallize and binders firm. Cooling profile is staged to prevent cracking. Rapid surface cooling can create a hard skin while the core remains soft. A staged profile cools evenly and yields a uniform firmness for cutting. Moisture control is critical in both styles. Oat bars sit in a moisture window where they are not sticky but still chewy. Too much moisture leads to stickiness and microbial risk. Too little moisture leads to hardness and crumbling. The process controls this window through binder solids and oven time or cooling time. Water activity is measured on samples and used to adjust settings. After baking or cooling, the slab may be conditioned before cutting. Conditioning allows temperature and moisture to equalize across the slab thickness. This reduces internal stress and prevents edge cracking. Conditioning also stabilizes the surface so blades do not drag. For baked slabs, conditioning can include a short cooling stage to bring the slab to a consistent cut temperature. Cutting converts the continuous slab into bars with defined weight. A first cutter trims the edges because edges can be uneven from spreading. Trim is collected for rework depending on recipe constraints. The main slab then passes through a guillotine cutter that creates long strips. A cross cutter then divides strips into bar lengths. Blade speed and sharpness are tuned to avoid tearing oats. Warm slabs can smear and stick to blades. Cold slabs can fracture and generate crumbs. If the product includes a top drizzle or enrobing, the coating step can occur after cutting. Chocolate is tempered and then applied as a curtain or as a drizzle. Drizzle heads deposit controlled lines. Enrobing coats the bottom or full bar. Coatings are then set in a cooling tunnel. Coating application must avoid adding excessive heat that softens the bar matrix.